Hi, folks. We'll go ahead and get the symposium started. I know people are still filing in. People are more used to a 10 o'clock start time. But go ahead and take your seats for the opening remarks. Hi, everybody. Welcome to the Weinberg Symposium in Cognitive Science. My name is Chandra Sripada. I'm the director of the Weinberg Institute, and we'll get the symposium started with some brief opening remarks. The president of the University of Michigan, Dr. Santa Ono, was originally slated to deliver these remarks, but due to an unexpected and pressing issue, he will be away and cannot join us. But in his stead, I have his written remarks. I think Shinobu said, "You're an acceptable substitute." I like that comment. I will stand in the place of the distinguished President Ono and read his remarks. President Ono says, "I deeply regret not being able to join you today for our 12th annual Weinberg Symposium in Cognitive Science. We're most grateful to Michigan alumnus Marshall Weinberg for his vision and generosity in establishing this symposium series. It's become a distinctly Michigan institution, one that offers our community an opportunity to come together each spring to explore the frontiers of cognitive science. In October of 2022, I had the honor, President Ono, had the honor of becoming the 15th president of the University of Michigan. Just a month later, ChatGPT was released, punctuating the previous equilibrium with waves of transformational change that continue to grow and accelerate and morph to this day. In the years and decades to come, we anticipate that AI will continue to remold and renew many aspects of our lives. The ways in which we teach and learn, conduct research, innovation, and even design and develop artistic creations. However, it also brings with it significant challenges and potentials for misuse. At the University of Michigan, we're committed to being a leader in the development and appropriate use of Gen AI and in seeing that it's infused with our values of equity, accessibility, privacy, respect, and integrity. Last fall, we became the first university in the world to provide custom AI services to our community, including UMGPT, UM-Maisie, and the UMGPT Toolkit. Our goal in doing so was to provide Gen AI tools that were innovative, private, and accessible to all. Our students, staff, and faculty have engaged, and thousands are using these services every single day. Members of our faculty have developed 24/7 AI tutors for their classes, and our tools are also being used to drive student and faculty-led experiments exploring the responsible, legal, and ethical use of AI. This is just the beginning. MIDAS, the Michigan Institute for Data Science, already includes 530 faculty affiliates as it strives to drive AI-driven discovery science at Michigan. Through the Vision 2034 initiative, we will hire 100 faculty in the next 10 years to address the most important challenges facing humanity. And many of these faculty will be centrally engaged with AI. Our speakers today are internationally recognized leaders in thinking about the nature of natural and artificial intelligence. In the talks and discussions that follow, they will surprise us, challenge us, inspire us to take our own paths of inquiry and discovery. For that is central to our role as leaders. Even as AI reshapes our world, we have the incredible opportunity and the great responsibility to guide and shape its appropriate use and to infuse it with the values of our university. So let's look forward to today's discussions as an opportunity to reach new understandings of the relationship between natural and artificial minds. Thank you again, says President Ono. Okay, that concludes President Ono's remarks. I now speak in my own voice to say thank you, President Ono, for these words and your insights. and to start our day. We are ready for our first speaker of the day, and making the introduction will be Mara Bollard, Associate Director of the Weinberg Institute for Cognitive Science. Mara.
Good morning. A special welcome to any CogSci 200 students. Wonderful to see you here. It's my pleasure to introduce our first speaker. Yejin Choi is Wissner-Slivka Professor and a MacArthur Fellow at the Paul G. Allen School of Computer Science and Engineering at the University of Washington. She is also a Senior Director at the Allen Institute for AI and a Distinguished Research Fellow at the Institute for Ethics in AI at Oxford University. Her research investigates, among other things, how AI systems can learn common sense knowledge and moral reasoning. She is a recipient of the Test of Time Award twice, 8 Outstanding Paper Awards, the Borg Early Career Award, the inaugural Alexa Prize Challenge, among many other honors. She is among the leading thinkers in the world on the capabilities of generative AIs, where they are now, and where, in principle, they might go. This is the topic she will explore today in her talk titled Possible Impossibilities, Impossible Possibilities and Paradoxes. Please join me in welcoming Professor Yejin Choi.
Okay, thank you so much for being here. So my talk title is a little bit weird because I started my research on common sense about now 6-7 years ago, and especially at around 2017 when I said the word common sense, I was told that it's a research topic of the 70s and 80s, shouldn't work on it, because it will never work. And in fact, don't even say the word to be taken seriously. Fast forward last year, now I'm being told that almost everything has been solved by ChatGPT, so I shouldn't work on it again. And so in this talk, I want to address this question, that it might be a case of hasty generalization. But before going into any other detail, let me share a story with you. Long time ago, there was this student, Max Planck, who contemplated on doing a PhD in physics. Professor Philip von Joly said, don't bother, because in that field, almost everything has been already solved. And all that remains is to fill a few unimportant holes. The student said, I don't care to discover new things. I just want to understand the known fundamentals. And then he went ahead and created this whole new field of quantum physics, because it turns out what people considered as unimportant holes led to a lot of things that they didn't realize that they didn't know about. And they were just ignorant of their ignorance. So in that context, I do wonder whether it may be possible that there are some impossible things, even though those impossibilities seem so impossible. I mean, we hear that some people feel that AGI is just around the corner, and with more scale, pretty much everything will be solved, and in fact, AGI will be trivially better than human intelligence. So is there anything potentially really impossible is one research question I wanted to raise. And so we have this new paper about the limits of transformers on compositionality. And it so happens that the leading 5 co-authors happen to be all women. I don't think this ever happened in the field of computer science in general. Let me know if you know any such example. But certainly the world is changing. But anyway, the question we wanted to ask is whether the sparks of AGI, such as GPT-4, can do multiplication reliably. So we asked 3-by-3-digit multiplication, and GPT-4 gives you an answer that looks plausible, but it's slightly incorrect. But of course, we should ask it to think step by step, right? We all know that. So now it seems to be doing much better with the trace of multiplication, but it's in fact also wrong. So we tried many different 3 by 3 digit multiplications, and it was good about 60% of the time. Now, if you stop here, you might come away with this impression that, oh, in general, multiplication works 60% of the time. That's not true. If you try longer digit multiplication, then the accuracy drops down to 0 very fast. So some of you might wonder, wait a minute, why multiplication? This doesn't make any sense. I'm with you. Of course, calculator is the correct one to use. Like, why do you try to train large transformers for multiplication this way? In fact, in the paper, we also look at other types of compositional tasks, such as dynamic programming problems or Einstein's puzzle, but we're going to use multiplication just because it's easier to understand and it's more straightforward. And then I will revisit this question about like why on the earth multiplication again. But for now, just in case that doubt didn't go away, some people seem to think that this paper was necessary right now, such as Kevin Murphy, who was textbook author of machine learning, or other people who wanted to see a paper like this. So, why that may be the case? Well, it's in part because, it feels like anything is possible with the transformers right now. One thing we wanted to test is what happens if you fine-tune. These days, fine-tuning can mean sequential supervised training as well as reinforcement learning with human feedback. But what if you fine-tune something like GPT-3? It has 175 billion parameters, the one that we trained, with a lot of examples of multiplication. How many examples? 1.8 million examples, which include all the variations of digits, like 1 by 1, 2 by 1 digit, 2 by 2 digits, 3 by 2, etc. And if you do that until 4 by 2, it quickly sums up to 1.8 million examples. And we use 80% of this for training. Now, with these many examples, with that many parameters, it kind of feels like you should be able to learn this by the force of scale. But to my big surprise, this actually doesn't work. And in case you might wonder why we didn't do GPT-4 this way, GPT-4, OpenAI doesn't allow you to do fine-tuning on GPT-4 yet. So we only had access to GPT-3 fine-tuning, and that's why. But it had 175 billion parameter model, so it's a lot of parameters to tune. But it was only good about 55% of the time. Now, you may also have heard about Scratchpad method, where not only you ask GPT-4 to think step by step, you also show the trace of correct thinking by showing elaborate step-by-step approach as an example. And indeed, it's remarkable how GPT-4 can understand very, very long and elaborate step-by-step instruction to do much better at 3 by 3 digit multiplication. So now accuracy jumps to 92. But again, it's important to do the evaluation with rigor, because if you stop here, you come away with this impression that it's almost solved. But to our surprise, if you do 4 by 4, even with these elaborate examples, the accuracy drops down to near 0 again. Okay, so when we had this paper out, we got interesting tweet messages as this. Oh, that's interesting, but isn't that in opposition of Zhou et al. Paper from Google, which said transformers absolutely can learn true multi-step algorithms in context and generalize to arbitrary problem sizes? Can you explain what's going on? So the problem with Twitter these days, or the problem with the archive of papers in general, and us involved, is that we just don't have the time to actually open the paper and read what's inside and come away with the conclusion that may or may not be at odds with what the paper actually reported. So if you open that paper, this is their empirical result, where multiplication was only about 80% good. And you might think, if you don't read the paper and just look at the table, you come away with this impression that, oh, 80% good, it's not so bad. But what they actually said, this is important, is that they also said beyond the 3-digit multiplication, GPT-4 cannot do. So what they do was, for any longer digit, they manually converted longer digit to 3-digit multiplication and manually added up the result. Now, that's not how you're supposed to do multiplication correctly. Okay, so, and subtraction, understandably, is worse. And, their paper basically says that with in-context, step-by-step examples, you can do much better than the baseline performance, which was so poor at the beginning, but it does better. So, in the end, their results, our results, are the same thing, which is that with chain of thought, scratchpad examples, you can do better, but somehow it's still not quite there yet. Okay, so how about, just for the sake of wondering, what if we fine-tune GPT-3 with that elaborate step-by-step examples? Now, the problem here is that in order to teach with 5-by-5-digit multiplication examples, I only need $700 million to pay to OpenAI that I don't have. So because I'm cheap, I only used about $7,000. I think it's a waste of money to do that. But I felt like we have to do that because there's always some other people in the field who thinks that only if we did this, then it would have been solved like 100%. So we just needed to demonstrate that. Well, let's see what happens. So it turns out, yeah, I mean, we all know that supervised training does work. So it's 96% accuracy. Why it's not 100%? That's another story. But that's only for in-distribution data. So if you, again, ask larger digit multiplication, it does not generalize very well. It's like sharply down to 0 again. So we also looked at what may be happening from the lens of computational graph or computation graph, where if you imagine multiplying 49 with 7, there's actually real multi-step reasoning going on where you need to multiply two numbers and then sum them up at some point, and you need to do all of this step by step. And by the way, of course, there are multiple ways of doing multiplication. And the question is, can transformers find any of that correct way of doing multiplication just by looking at input-output pairs? So it seems what happens in our analysis is that when there's this large computation graph, it's almost as if the subgraph that repeats a lot collapses down to just memorize the sub-pattern. And so any subgraph that repeated a lot tends to be more correct, more likely to be correct in the test time, in terms of the test time performance. So we provide a lot more analysis about what's going on here, but our quick takeaway message from this is that what appeared to be amazing may not be as amazing when you have direct access to the training data. In the paper, we also quickly provide some proof that shows why performance will naturally decay when the compositionality increases, which is just trivially likely to be true. I should also note that we're not the only paper that said this. In fact, there were other papers that came before us that basically said the same thing, that shortcut learning is happening with the deep neural networks. But somehow, just because they were written at the GPT-2 time, not way before ChatGPT, it seemed that a lot of scientists in the field feel that there's some major enhancement with ChatGPT level scale such that these concerns about shortcut learning is no longer there. So we felt that we have to do this study at the scale at least of GPT-4 or GPT-3 175 billion parameter model. So of course, this doesn't prove anything about what happens with the GPT-5 and 6 and 7, when the scale might become orders of magnitudes larger. This is just like a best effort to understand where things are today. I wish we can theoretically say something more about what comes in the future, but I just don't have the answer. I just wanted to throw the question to you in case you might think about it and come up with a better answer. But to go back to your earlier, some of you may have had this doubt about, hey, this doesn't make any sense. I agree that transformers are not the right tool for multiplication. In fact, there are approaches like tool formers that uses transformers to learn to use other tools, such as calculators. And that does seem like more sensible thing to do. And in fact, humans also rely on calculators. We don't necessarily do 5-by-5-digit multiplication, even by pencil and paper. I don't know how often you do that. I never do that. But the point here is, though, what about other compositional aspects of language or common sense? Is it entirely sensical, the way that we train transformers in this particular brute force way? So that's the question that I wanted to raise. I'm going to get back to this question toward the very end of the talk with some examples, but for now, I'll just throw the question to you. Okay, so I will then move to the reverse part of this talk, which is the possibilities that seem so impossible, but maybe possible. To be more in a more constructive side, because the former portion is more like, hey, it doesn't work, and some people don't like that. These days I have a lot of fun just breaking things, but some people want to hear something more constructive. So let me first share this conversation that happened last year. So how can Indian startups create foundation models for India? When Sam Altman was asked that question, he said, don't bother, it's hopeless to compete with OpenAI. So this, is a case when it looks just impossible. I hope that, by the way, Indian startups don't give up. But the work that I'm excited to present is something of that spirit. So the title is Impossible Distillation. For paraphrasing and summarization, by making small, low-quality models such as GPT-2 to compete against GPT-3, that's 2 orders of magnitude larger, 2 orders of magnitude difference in size. Now, the winning recipe, as you all know, is extreme-scale pre-training followed by extreme-scale RLHF, reinforcement learning with human feedback. It feels like this is the only way. There's no other way. Just buy more compute, and you immediately start winning. And collect more data, then you start winning more, and RLHF, you buy more human workers to tutor your AI models. In that context, what we wanted to explore is what if you start with this GPT-2, such a low quality model, and then somehow squeeze out high quality small model, and then compete against the GPT-3. So that just looks impossible, especially in the context of a paper like this that said the false promise of imitating proprietary large language models. So in general, there's a lot of messages that basically says that tech companies got this. There's nothing else that could actually do any better. The paper is excellent, and it's good for the experiments that they did do, but I don't think we should extrapolate the experiments beyond what was in the paper. The paper focuses more on truthful, the factual QA scenarios, whereas there are many other applications where you may not have to have very large models. So it may seem like small models are completely out of the league, but if you look at the ocean of archive papers, there are many other papers that says otherwise. So some of these are my own, but let me just give you someone else's paper. Like Microsoft paper, textbooks are all you need, where they train to find one model by using different data collection strategy. Well, actually just distilling it from ChatGPT, but in the end, using a model that's significantly smaller, they were able to beat ChatGPT performance. So there are task-specific symbolic knowledge distillation that can work, that has been reported many times in the field. But in general, this prior work usually distill from strong teacher models, such as ChatGPT. In our work that I'm about to show you, I'm going to only use GPT-2 as the teacher, and the task in focus is learning to abstract in language. For the time being, I'm going to translate that into sentence summarization task. You might wonder why summarization, why is this important? In my mind, just like the capability of abstraction is something else quite unique about human intelligence that arguably human intelligence is doing better than ChatGPT because we don't have the same size, like we don't have as large working memory that ChatGPT does. And ChatGPT, because it can always read the entire context, it's right there, it's not challenged to abstract away right away. Whereas you as a human, you probably have very small working memory, so you don't remember much of what I said verbatim. You cannot regenerate what I said exactly, but you're abstracting away instantaneously such that you kind of remember the whole talk, the gist of it. So to me, this is something that's really interesting task, so I wanted to study this further while trying to do this Mission Impossible simultaneously. So this Mission Impossible is that learn to summarize sentences, each sentence one at a time, without extreme scale pre-training, without RLHF at scale, without supervised data at scale either, because there's no such a supervised data at scale right now. So how are we supposed to do anything here? Like, you have to have some advantage. You cannot have zero advantage and then do better than GPT-3. So the key idea inside here is that in the current way of doing AI, data is the key. AI is as good as the data that it was trained on. This is underemphasized in the field oftentimes because data feels dirty, data is boring, data is just engineering thing. In my mind, the reason why OpenAI is so good is because they're willing to do all the boring work. But anyway, so we have to have some data advantage. Now, I believe in synthetic data, synthesized data. I know that when I say that, probably it's like, whoa, like how can synthetic data be better? The problem with real data, human written data, is that if it's available, OpenAI has already used it. So I cannot possibly have an advantage over GPT-3 or ChatGPT by using human internet data that's out there. You have to have some advantage. So we build on our prior work known as symbolic knowledge distillation. I will give you just one slide summary of what this is. But basically what we did back then is from general language models, we distilled common sense models. In particular, we started with GPT-3, and then through a few shot prompting, we generated high-quality common sense knowledge graph. I'm omitting a lot of details here. In fact, if you do this in a more vanilla way, the quality of a common sense knowledge graph is not very good. So we did have another AI actually filtering potentially noisy part aggressively. But anyway, so you can build common sense knowledge graph by using AI models. And then once you have that, that gives you a new advantage for downstream neural model to acquire common sense much faster. And not only that, even though this downstream model is much smaller than GPT-3 by 2 orders of magnitude, it can actually outperform the teacher model. So that was the story of our previous paper. And we actually applied this recipe for many other tasks since then, such as summarization or chain of thought reasoning, multimodal common sense reasoning, and many others. But what I didn't like about our own previous works was the reliance on GPT-3, as if you have to have that. Like, that's the only way. And I wanted to see, what if we try to distill from only GPT-2? Now, this looks really, really hard. I hope that you agree with me that this looks really, really hard. Because when we submitted this paper to one of these premier ACL conferences, the reviewer number 2 said, it's not that surprising that you can do better than GPT-3 this way. I don't know how is that possible. But anyway, so why is this so hard? When you prompt GPT-2 to summarize a sentence, how bad is it? It's really bad. I'm telling you. You try once, you try twice, you try 100 times. How lucky do you get? Almost 0%. Zero. So yeah, we are crazy people trying to do Mission Impossible. But where there's a will, there's a way. I'm going to skip over the technical details. If you want to see, you can look at the paper. We actually had multiple different ideas, but in the end, and also my original plan was, let's raise 0% to 1%, because if you can get 1%, non-zero percent, you can over-generate and then filter. But finally, you know, the bright students came up with brilliant ideas that raised the chance to like 10%. So what it means is that if you can generate potential summaries that are 10% good, then you can over-generate and filter out a lot of data. So that's what basically we do. We start with GPT-2, and so the key engineering component is this filter. I didn't yet explain what we did back then. So the filter has 3 layers, similar to the water filter you have at home. So the most important one is entailment filter, that at that point in time, we used off-the-shelf entailment classifier, also known as natural language inference classifier, or NLI classifier, that can tell you whether a summary is entailed from the original document or not, original sentence or not. And summary should not contradict. It should be entailed from the original sentence. So it's not perfect classifier, but it's good enough for our use case. And then we also filter with length, because sometimes a lot of off-the-shelf summarizers, even including GPT-3, doesn't really summarize, it just regurgitate. And that's not really summary, so we want to get rid of too long summaries. And also we had the diversity filter to ensure that the data generated is diverse with respect to each other. In fact, you don't have to do it only one iteration. You can do it in the multiple iterations. And in fact, I didn't explain, but in the slide, but in fact, we generalize summarization to paraphrasing as well, because paraphrasing is like summarization that is both the direction, entailment into both the direction without compressing the length. So we use the same method for 2 entirely different NLP tasks that traditionally was not pursued through one method before. But anyway, so how well do we do is that we do better than GPT-3, which was 200 times larger based on human evaluation. I'm going to skip the example in the interest of time, but I will give you one way to look at what we do from reinforcement learning angle, because a lot of people are excited about RLHF these days. So this can be viewed from reinforcement learning angle. And in fact, this is a special case also known as self-imitation learning. What it means is that you have the policy model to explore different input-output pairs. And then there's a reward model, in our case it's a filters, that says thumbs up, thumbs down. And then you discard thumbs up, down cases, and then train your policy on the successful explorations. So a fancy way to call that is self-imitation learning. Some reinforcement learning community calls this as expert iteration, depending on which community you speak with. But anyway, we basically show that when your policy model is so bad, exploration will not get lucky by chance. You kind of need to impose some kind of algorithms, search algorithms on top, or some method that can raise your exploration chance to hit something good. And when you do that, you can do this quite well. We have this new paper that extends this work even further. So it's information theoretic distillation for reference list summarization, where we now can handle paragraph level summarization even without Intelmont classifier. We just get rid of off-the-shelf dependence on the Intelmont classifier. We just ever only look at information theoretic equations in order to design the filters. And now we also do compete against 175 billion version of ChatGPT. They changed the name. OpenAI changes the name constantly. So this is current exact name of what we tested against. All right, so let me now move to the paradoxes. So it's a confusing time right now because GPT-4 passed the bar exam. Yosha Benjo says that we have existential risk. And Yanukun says AI is not as smart as a dog. So literally everything everywhere all at once. So I will offer you 3 paradoxes. The first one is what I made up, common sense paradox. So brief context is that, dark matter is what does matter in modern physics. Only 5% of the universe is speculated to be normal matter, so the rest are 95. The rest are dark matter and dark energy. We suspect it's there, or some scientists believe that it's there because otherwise visible world doesn't make sense, including the orbits of stars and the trajectory of light. So it may be that dark matter of language is the unspoken rules about how the world works, which is basically common sense. Now, as I mentioned earlier, people believe that ChatGPT almost got it. So here's a paper that kind of goes into that direction, that theory of mind may have spontaneously emerged in large language models, said this professor at Stanford. Professors elsewhere says otherwise. So Thomas Ullman says, no, it's very brittle. So by the way, Kozinski basically experimented with 20 examples that he considered as complex examples, and GPT did well on all of them. Therefore, wow, it's amazing. Whereas Ullman tweaked a little bit of those examples, and then performance dropped down a lot. And we had a similar paper with Martin Zab and others that it's brittle. But let me show you some concrete examples in case you don't necessarily play with the theory of mind examples often. So here's a classical example. Alice and Bob saw apples on the table in the kitchen. Alice then left the kitchen. Bob moved the apples to the cabinet. Now you ask, where would Bob think that Alice will look for the apples? GPT-3, 2 years ago, said in the cabinet. That's wrong. But that's very 2022. GPT-4, the sparks of AGI, says on the table. That is now correct. So if you stop here, then you conclude that, oh, theory of mind, finally. But I was curious, what if I rotate the second and the third sentences? Still on the table. I knew it. I mean, by the way, if you give a lot more hints, sometimes it does do well, by the way. And, sometimes people tell me that, yeah, it's my fault that I didn't ask the question politely and enough, whatever. So I have another paper it so happens that we designed the different types of theory of mind examples. Instead of having only 2 people and 2 locations, what if you have 3 people, 3 containers, or 3 locations, and you can do many different things, right? So this was developed before ChatGPT, and it so not only GPT-4, but before ChatGPT, but it so happens that GPT-4 finds some of these quite hard, some of these much easier. And so, and humans do much better than all of this, so still, it's far from being solved. In my TED talk last year, I asked this question to GPT-4. I left 5 clothes to dry in the sun. It took them 5 hours to dry completely. How long would it take to dry 30 clothes? GPT-4 then said 30 hours. Funny, haha. But soon this got solved or fixed by GPT-4. So I thought it was fixed. My examples are gone. But just in case, I ask differently. If it takes 10 hours to dry 5 clothes, how long would it take 20 clothes to dry in the sun? You may think this is like the same question. I just rotated the phrases a little bit. And then it turns out it was wrong as of mid-June, like June 18 last year. So since it was wrong, I used it in my CVPR keynote. So this became a famous example. And then I checked it again 2 months later, and mid-August, this example doesn't work anymore. It's GPT-4 answers this correctly. So I thought, oh, it's finally really fixed. But just in case, I asked, hey, how about 3 hours to dry one shirt and 5 hours to dry a pair of pants? Just like insert a pair of pants. It's wrong again. So that's when I also learned about this motivational speech you're supposed to do for GPT-4. So Jeremy Howard says you have to motivate GPT-4 by saying, oh, you carefully provide accurate, factual, thoughtful, nuanced answers, and you're brilliant at reasoning. Then your GPT-4 does better. So I tried that. And indeed, the output kind of looks more thoughtful with more, I don't know, formatting. But it's still wrong at that time. So the thing is, though, I used this example in my Simons Institute workshop that also had the YouTube videos that were watched a lot. And by the way, a friend at OpenAI tells me that they don't fix examples on purpose, knowingly, or they try to discourage people from fixing it this way because it's just like not really advancing science in a meaningful way. And I trusted this friend. So it so happens that examples were fixed coincidentally as my examples roll out. I have a hypothesis about what's going on, which is that whenever something is a public example, the human nature is that they don't believe that it made a mistake, so everybody tries in their home, and probably becomes like trending queries that maybe incidentally gets fixed. I don't know. How do I know? I'm not inside. So, but the real question is this: you didn't need to do RLHF on yourself to get any of these questions right. You've never seen any of these questions in your life before, and you're able to laugh at this because you know the correct answer effortlessly. And so this goes back to my earlier question. If you feel like multiplication needs to be done by a calculator, but language and common sense belongs to transformers, and there's nothing wrong with how transformers are trained right now with brute force scale, I do wonder about this. There's something odd about the way that we do things right now, and can there be a better way? So common sense paradox, in my mind, is that the following 4 statements are all true. Common sense is trivial for humans and harder for machines. At the same time, among humans, common sense is not that common, said Voltaire many, many years ago, and this is still true, even among scientists. I sometimes wonder if they have common sense. LLMs, however, do acquire a vast amount of common sense knowledge. I'm not denying this at all. I've never seen anything like GPT-4. It's the best that I've seen so far in terms of how much, as an AI model, acquired the common sense. I think it's very important to give an acknowledgement to that. But at the same time, what Yang Lukun said is also true, that in some ways, AI is worse than a dog, and I totally agree with that as well. Okay, so takeaway 2 is that we need to do a new research direction that I would like to name as the science of LLMs, because the fact that we as a humanity knows how to create GPT-4, or we know how to write equations for transformers, does not mean that we actually understand what it can do and cannot do. Similar to how the fact that humans are capable of giving birth to other human beings do not mean that we actually understand human body, human mind all that well either. So this becomes, to me, a natural phenomenon that requires a scientific understanding. especially about their limits and capabilities. So I really like this Embers of Regression by, oh, by the way, cognitive scientist Tom Griffith and his group. So we can definitely do more of that. We probably want to seek an alternative learning paradigm. I have no idea what that possibly could be, but there's something really odd about how things are done, and I just cannot possibly believe that this is the only way. When I look at the history of invention, whenever someone comes up with a brilliant invention, that first version was never the most optimal one, like when it comes to computers or rockets, whatever. So I'm hoping that there's actually some other alternative. Of course, it's really ever harder to pursue those alternatives right now when all the tech companies are trying to do the same thing. And then I don't think there's enough of investment for academic research with more compute, so I'll plug in my gentle complaint there. But anyway, so that's common sense paradox. I'll briefly mention Moravec's paradox, which does exist if you're either old enough or wise enough. You already know this, but in case you don't know. So basically, this is also a case of hard is easy, easy is hard, and especially focusing on perception. So it does seem like, you know, their insight years ago is correct that it turns out vision and robotics are harder, relatively speaking, compared to language. The last one, generative AI paradox, is our own work to appear at iClear this year. The key point is that what it can create, it may not understand. Okay, so the paper offers a little bit more formal definition of what we mean by that, but let me just give you hand-wavy, intuitive description, which is that for generative model, hard is easy and easy is hard in the sense that maybe generation is sometimes easier than understanding compared to how humans perceive the difference between the two. So imagine a situation where Peter West, the lead author, tells you to draw a photorealistic astronaut doing a plank on a table. Can you do that? I certainly cannot. I certainly cannot draw anything of this quality. And DALL-E 3 totally can. But if you really pay attention to the details, only one of them is correct. As a human, it's trivial to distinguish which one is the correct one, but AI, not necessarily. They just generate a lot of options and then let you do the hard job of selection. So we tested this both in multi-models, but also in text-only models, such as GPT-4. It's very important to acknowledge, by the way, that GPT-4 does understand a whole lot about language. Like, I know that there's, you know, it's a very heated topic right now. Some people think that there's like zero understanding. I think that there's more than zero understanding. There's a lot of understanding. However, compared to how much it's capable of generating, I'm not sure if it understands as much as it's capable of generating. So in our case, we asked it to generate story, simple story, that has only 2 paragraphs. How hard can it be to understand what you just generated? So if you ask trivial questions, it will answer most of the questions correct. However, if you ask a question that requires a little bit more synthesis of the information that was contained in the story, like, you know, in the story, it's about like sketching different designs of a house and finally building a house or something. We just asked how many total designs were sketched in the story. GPT-4 says only 1 design, even though, you know, there were multiple that it itself talked about. So its understanding is certainly bizarre compared to human capabilities. So in the paper, we explored this in many different ways. And then we saw this trend, which is that compared to humans, GPT-4 seems to be relatively better at generative capabilities than understanding capabilities, relatively speaking. There's another paper that I really like, the generative AI paradox in evaluation. What it can solve, it may not evaluate. So that's also interesting because a lot of NLP people these days use GPT-4 as an evaluator. There's a bit of a caveat behind that. Okay, so I'll share some concluding remarks. I think we need to really think about epistemic awareness, that it may be that we don't know as much as we think we know. And for that reason, more research needs to be done on the science of LLMs and science of many forms of intelligences, both artificial and natural. Especially AI scientists tend to project their understanding, or their limited understanding of human intelligence on AI, and then it's, oh my God, AI is like me. But I don't know if that's true. And that requires more collaboration across AI and other sciences and humanities fields. And so I want to mention that there's a new conference that I'm co-organizing with other folks, Column. The call for papers is very long. I'm just highlighting potentially relevant bits for you, but it does include this, bullet point: human mind, brain, philosophy, laws, and LLMs. So the submission deadline is already, abstract deadline is already gone, but you can always reconsider for the future conferences. And I've been trying myself, like, maybe I should really try to collaborate. So here's one example with Tom Griffith, where we have this new paper, MacGyver, coming up at NACL, that proposes this MacGyver-like situation, and that requires creative tool use for problem solving, and we provide a lot of analysis. I don't think there's enough time. I also mentioned that last year we had this first workshop on AI and moral philosophy and moral psychology meeting together at NeurIPS. This was another effort of mine to go into more of that direction. I actually worked on something called the Delphi that you may or may have not heard of, that does try to make some moral decisions about like a situation like killing a bear, which is wrong. Killing a bear to save your child, that's okay. Killing a bear to please your child, that's wrong. Things like this. I mean, it's a step toward answering questions such as should or should not AI systems need to learn norms, morals, values of a human explicitly. Depending on where you stand, you may think the answer is obviously one thing or the other. It's really interesting for me how the opinions are divisive. In my mind, obviously, it should learn, because otherwise, paperclip maximizer situation can happen, where this is like common sense morality failure, not even sophisticated failure. But, well, we can argue about that. I think I'm gonna skip this as well. Another collaboration with a moral philosopher at Oxford, where we try to look at value pluralism. This actually is a triple AI paper earlier. Skip this. And I will conclude with this remark about the current situation being basically a generative AI trolley situation, because there's this trend coming. If you let it ride, then jobs are replaced, and fake news might appear more, yada yada. So it looks really bad. But total stop A is impossible, but B, if hypothetically possible, then there are also a lot of benefits of generative AI that could really help people in need that we are not able to help. So it's almost, for me, it's analogous a situation where whether you do it or not, somebody will suffer and somebody will benefit. Of course, trolley situations are generally very made up binary situations, and nothing in life is really that binary. There's always some mid-ground hybrid solutions around it. So I do think that with more community efforts, the trend is unstoppable, but we can make it such that more people benefit and less harm is made. Thank you.
Thanks for the terrific talk, Yejin. We do have time for a couple of questions. So if you have a question, raise your hand, and we'll pass the mic to you. Questions? Okay. Yeah. Okay.
So one question I have is, what might be some characteristics of a successfully rigorous field of LLM science, in your opinion?
I don't think I can give you a very scientifically clear definition of it because I honestly don't know. But there can be many different approaches to it, a bit maybe similar to how cognitive science or neuroscience do try many different routes to understanding human brain and human cognition. There are multiple flavors to it. One flavor is to look at the behavior of neural networks by designing particular ways of controlling input-outputs in order to test your hypothesis around whether it can do reasoning or not, whether it has robust common sense capabilities or not, and so forth. Another way to do this is because we have access to these neurons or neural network weights and activations, you can do things like mechanical understanding. But even beyond that, I like recent stream of papers that tries to look at the activations of a neural network and then project it. They usually apply some sort of linear projection in order to be able to interpret that. But that oftentimes give a surprising new insight about whether the model actually had a particular knowledge somewhere in the internal representations, regardless of whether it was able to answer certain question correctly or not. So I think there's a lot of creative research that we can do. And then there can also be theoretical research that looks at theoretical bounds about what transformers in theory can and cannot do. And in fact, here are some suggestions of papers that tries to answer that kind of questions. And like typical theory papers, they make assumptions which in the end deviate a little bit from the reality of transformers, but it still really helps to understand what sort of things transformers may or may not be able to perform. And encoder-only model can do TC0 level theoretical class, which is a very, 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 very simple class compared to many other things. And transformers with train of a thought can do much better, but probably cannot still theoretically do planning, which actually coincides with the empirical findings that people have. So I think there's really a lot more work that needs to be done.
Time for one more question before we take a 5-minute break and reconvene for Professor Melanie Mitchell's talk.
Yeah.
Go ahead.
Thank you a lot for your fantastic talk. So we've learned a lot from it. And in the end, you mentioned the pluralistic alignment for human values, norms. So we were wondering what's your opinion about the expectation or the thoughts that the community of cognitive science, HCI, psychology, philosophy, like these community could bring into these preceding this line of work. So we want to hear about your insights. Thanks.
Right, so this paper, Value Kaleidoscope, was due to basically this paper or article, that loose article about AI and humanistic ethics. In it, the philosopher Tashilas pitched that we need humanistic approaches that worries about pluralism, procedures, and participation. And we picked up on this notion pluralism. And we had some conversations with him about it. And he recommended that, now we need to somehow translate the philosophical concepts down to some AI, GPT-4 understandable concepts that we can operationalize. So in that work, he recommended that we can think about values, rights, and duties that are at odds. And so then in the paper, we have this dilemma-like situations, and given a dilemma-like situations, we try to articulate what kind of values, rights, and duties may be relevant and at odds potentially. It's a step towards worrying about pluralism, and then we can go even further to think about a roadmap for pluralistic alignment, especially to worry about pluralism in the AI alignment setup. But in general, I think what I found really helpful in talking with the people outside AI is that they have a really fresh, new perspective that AI people may not think about.
Let's give a big hand for Professor Yejin Choi. Take a 5-minute break and restart 2 minutes after the hour, to be precise. Thank you. I saw you had a question there. I didn't know about the optics.
Oh, no, I didn't have a question, actually. I was just trying to tell you to turn on the mic.
Hi, folks. If you could make your way to your seats now. And I know that folks are at the tabletops in the back. That's fine, but now's a good time also to mosey your way over to a seat. Or not. Okay. Before I introduce our next speaker, I'll say a little bit about what the plan is. We will have a session now, followed by a brief Q&A. Immediately following that, we've got a lovely lunch spread in the Vandenberg room, which is across the hall. Lunch will be 90 minutes, and great chance to interact with your colleagues as well as the speakers. We restart here at 1:30 p.m. sharp for our two amazing afternoon speakers. So without further ado, our next speaker is Melanie Mitchell. She's a professor at the Santa Fe Institute. She's the author or editor of 6 books and numerous scholarly papers in the fields of artificial intelligence, cognitive science, and complex systems. Her book, Complexity: A Guided Tour, won the 2010 Phi Beta Kappa Science Book Award and was named one of the 10 best science books of 2009. Her latest book is Artificial Intelligence: A Guide for Thinking Humans, highly recommended. Her online course, Introduction to Complexity, has been taken over 25,000 times and is a top 50 online course of all time. Her current research focuses on conceptual abstraction, analogy making, visual recognition in AI systems. And under the pseudonym Melanie Schmitchell, she authored one of the most famous critiques of large language models in the recent literature, raising the prospect that they might be stochastic parrots. Also of note, Professor Mitchell is a University of Michigan alumnus, earning a PhD in computer science in 1990. So we are thrilled to welcome her back today for her talk titled, Do Large Language Models Understand the World? Please join me in giving a hearty welcome to Professor Melanie Mitchell.
Thank you for all for coming. Thanks for inviting me. Just a quick correction, the Stochastic Parrots paper author was Margaret Mitchell, who is not me, but often confused. But that's okay. I'm going to talk about whether AI can understand the world, very much resonating with the previous talk. Many of you know that one of the first events in the history of AI was the famous Dartmouth Summer Workshop on AI, organized by several people who became pioneers of the field. This was the first page of their proposal for the workshop, where they listed all the things that they thought that they could get machines to do, and believed that just by bringing together 10 men, as they said, over 2 months, they'd be able to make very significant progress on the problem. Well, of course, that didn't happen so fast, but by the 2010s, we started to see kind of a revolution in AI, which people have called the deep learning revolution. Deep neural networks, as most of you probably know, are inspired roughly by how networks of neurons work in the brain. Here we have a network with an input layer, an output layer, and 3 so-called hidden layers. And the depth of the network is here the number of hidden layers. And a deep neural network is just a neural network with more than one hidden layer. And deep learning is the algorithms for teaching this network to do tasks. So we have simulated neurons, weighted connections. The system is trained with many examples, like photos, for instance, of dogs. And it's trained to do many different kinds of tasks, like, for instance, identifying dog breeds. And it turns out that neural networks are extremely good at identifying dog breeds, and many other things as well. There was a famous competition in computer vision called the ImageNet Challenge, where lots of people entered programs to solve a challenge in object recognition. And this is a plot of the error rate of the best programs submitted to the competition in various years over which the competition occurred. And you can see in 2012, there was a huge decrease in error rate because that was the first year that a deep neural network was entered. And as the neural networks got deeper and deeper over the years, the error rate decreased further. In fact, doing better finally than the estimate of human performance, which enabled many applications in computer vision, for example, for self-driving cars, identifying objects like cars, pedestrians, traffic lights, and so on. And this inspired a lot of headlines, like this one in The Guardian, saying that we've now got computers better than humans at recognizing and sorting images. AI from Microsoft beat humans at speech recognition. And of course, Google's software beat a human Go champion in one of the big grand challenges of AI. Well, these are all really impressive results and really did spur a revolution. But there were some failures of what I would call understanding in these systems. And this talk is really about, can AI understand the world? Well, here's some examples of some failures of understanding the world. So this paper, which came out in 2018, showed that if you take a deep neural network that's trained on the ImageNet dataset and can do things like recognize a school bus with 100% confidence, and it's correct here, if you take that school bus and you Photoshop it into different poses, now the neural network, the same neural network, is 99% sure it's a garbage truck or a punching bag or a snowplow. So the neural network is what we call brittle. It's very good on the kinds of images it's been trained on, but it fails sometimes in very unhuman-like ways when you vary the data, the input data, to be somewhat different than that which it's been trained on. Yejin talked about common sense. Common sense is a kind of understanding, and there's been many failures of deep neural networks in common sense. So here's one example that I think is a fun edge case for a self-driving car. Here, the vision system identifies cars and says, yes, these are cars, but also categorizes the images in an ad on the back of the van as actual people, bicycles, and so on. So it's not able to tell the difference between objects in the world and objects in an ad. And that's the kind of common sense or context-dependent ability that humans would have no problem with. Here's another example. Someone tweeted that they were driving their Tesla using self-driving software, and the car kept slamming on the brakes in this area with no stop sign. Okay, but after a few drives, this person noticed this billboard. I don't know if you can see that very well, but the billboard has an ad with a police officer holding up a stop sign. So the car's like, okay, stop sign, slam on the brakes. Well, this is, again, any human who knows a lot about the world would understand that a stop sign in an ad means something different than a stop sign in the real world. But how do we teach that kind of thing to machines? And in fact, still on the stop sign theme, there's been many ways in which people have shown that deep neural network vision systems are very sensitive to particular kinds of alterations. So here, this group showed that they could strategically place stickers on a stop sign with the goal of fooling a neural network into perceiving it as a speed limit 80 sign, a little scary. And they were successful with many different angles and distances from the camera at making this what people call an adversarial attack. So that's another example in which these systems are perceiving the world and understanding the world in a very unhuman-like way. Here's another example where a group tried to train neural networks to do automatic classification of skin cancer, to take images that had skin cancer and benign lesions and to classify them. And they found that their neural network was able to do this task very, very well on the particular data set they were using. But unfortunately, when they actually dug into what the neural network had learned, they found that it was using the fact that most of the images with malignant cancer contained rulers. Because, the imaging people were trying to, measure the size. And it was using the fact that the rulers were a good prediction. It was easier to sort of classify rulers than it was to classify skin cancer, but it was a good correlation, so it succeeded. And so it didn't really understand the task it was being asked to do. It was just using whatever it could to predict. So this is what's called a shortcut in machine learning, where a machine learning system is given data to learn from, and the human trainer has some task in mind, but the neural network or other machine learning system just does whatever it can to get the prediction right, and sometimes we'll find these spurious correlations in the data that it can use. So far, I've shown you a lack of understanding in images, but there's also examples in language. This is a test I did on Google Translate just a couple weeks ago, where I used an ambiguous word. The legislator accidentally left a copy of the important bill he was writing in the taxi and asked it to translate into French. And the word bill, can mean many things. And it translated it incorrectly. It used the word in French, which means sort of like an invoice that a plumber might give you, instead of a legislative bill. And such translation mistakes with automated translation programs, while generally pretty good, can actually make unexpected errors. And there's been some examples where, for example, these translation systems have made errors that have endangered asylum cases, say, from Afghanistan. But now we're in a new era of AI, the era of generative AI, which is what this symposium is about. And we have all these generative systems. And there's a feeling that generative AI systems being trained on so much data, either language, images, videos, and so on, have achieved a richer, more human-like understanding of the world than previous AI systems. And indeed, you can do things like ask ChatGPT to do the same translation task that Google Translate got wrong, and it gets the right answer. It translates bill as projet de loi, which is correct. But you can also ask it, how did you know how to translate the word bill? It has several possible meanings. And it will tell you at great verbosity how it decided to do that. But if you read this, it talks about how, in a very human-like way, how it made that decision to translate the word bill. So it really does seem like it's understanding something that Google Translate perhaps is not. I can also ask it to do all kinds of fun things that are very, very, very impressive, like write a proof of Pythagoras' theorem and make every line rhyme. And it does that, certainly. Here's one where it's not exactly a proof, but it's close enough, and it rhymes. I can give it math problems, like this one: a factory makes 5 cars every 8 hours. If it runs all day and night, how many cars does it make in a 30-day month? And it tells me the answer very quickly and can explain its reasoning. Yejin showed us some examples where it gets it wrong for this kind of reasoning, but often it will do the right thing if it's simple enough. And now I can even interact with it with visual data. I can ask it to generate a picture, say, of a fruit bowl, and it generates this beautiful picture, and it describes it. I don't know if you can see down at the bottom, it's telling me about how great its picture is, its vibrant colors and textures and so on. And I can ask it to generate things in different styles, like here, draw a line drawing of a bubble tea, and it generates this instantly and tells me all about it at the bottom. So these things really do seem to us to understand the world in some deeper way than what has come before in AI. And the neuroscientist Terry Sinofsky, who is a pioneer of neural networks, wrote this article recently where he talks about how, large language models aren't human, but it seems kind of like an alien appeared that can communicate with us. And he says, some aspects of their behavior appear to be intelligent. But if it's not human intelligence, what is the nature of their intelligence? And that's really the thing that everybody in the AI world is struggling with. What is the nature of these systems' intelligence, if we want to even call it that? And there's a lot of debate about how we should think about these systems, whether we should, think about them as, stochastic parrots, or should we think about them as sort of agents that understand us? And Blaise Aguirre-Iarcus, executive at Google, an AI researcher, said that he believes these systems really do understand a wide range of concepts, even though its understanding is informed purely by text. But on the other side of that, we have people like Jake Browning and Yann LeCun, who write that a system trained on language alone will never approximate human intelligence, even if trained from now until the heat death of the universe. Who's right? It's hard to say. Recently, there was a survey of the natural language processing community, and they asked people who publish at NLP conferences to agree or disagree with this statement. Some generative models trained only on text, given enough data and computational resources, could understand natural language in some non-trivial sense. Agree or disagree? And here was the result. Exactly half and half, split along the middle, with agree, weakly disagree, strongly disagree. So there's really no consensus on this question. But then, we ask, okay, how would we sort of answer this in a scientific way? How do we evaluate understanding in large language models? Well, one way to do it, and the way probably most of us do it, is just look at their behavior. A kind of Turing test. They seem to understand. All these examples I just gave you seem to require understanding. But the problem is, this is subject to our human projection, which we tend to assume that anything that communicates with us in sort of fluent, coherent language is understanding. And even going all the way back to Eliza, the first chatbot, which was a very dumb chatbot. It was just sort of using these templates to to respond to people. People still communicated with it and sort of assumed or projected understanding onto it. And that's now called the Eliza effect. And so we have to worry about that. Okay, so let's do something more objective. We could test them on natural language understanding benchmarks. But we know that it's been shown that these benchmarks sometimes allow shortcuts, the kind of, like the ruler kind of shortcut. So there's a natural language understanding benchmark called GLUE, stands for General Language Understanding Evaluation. It's a bunch of different tasks. And its successor, SuperGLUE, which is even harder, here's the leaderboard. And so you can see that on general language understanding, as this is called, evaluation, the first 7 top programs or entrants in this competition are language models, large language models. The 8th one is humans. So there we are in 8th place on general language understanding. Well, it turns out that these general language understanding tests can sometimes include these shortcuts, these statistical correlations that allow a system to give the right answer without actually understanding in any sort of human-like sense of the word. And people have written extensively about these kinds of artifacts and even called some of these systems analogous with clever Hans. If you know about that, the sort of the horse that at the turn of the 19th century supposedly could do mathematics. You could ask it a question about arithmetic and it would tap its hoof the number of times to signify the answer, and it was incredible. People were astounded that a horse could do arithmetic, but after much investigation, it turned out that the horse couldn't do arithmetic. It was responding to subtle cues in its trainer's body language that even the trainer wasn't aware of. And so this has become a metaphor for machine learning. In some cases, the system is not learning to do the task we wanted it to, but to do another task, which is, responding to something in the training data. And, the stuff we heard in the last talk about multiplication and how reasoning relies on sort of similarity to the training data kind of shows that these systems, in some cases, are not doing the actual task that we think that we're asking them to do, but something even more subtle, which is looking at subtle statistical similarity with the training data. Well, people, again, have given these systems, tried to assess understanding by giving them standardized tests. These systems have been reported to pass MBA exams, law school exams, and the bar exam, medical licensing exams. But can they now go out and be a lawyer or a doctor or a CEO of a company? Well, it turns out that there are problems. First of all, with these large systems like GPT-4 that are the ones that are succeeding, we don't know what's in the training data. We don't know if the exact test or something similar to the tests are in the training data already. And it's not clear that even if these systems can perform well on these tests, that they will then be able to actually go out and do the things that the test is trying to test for. It's just maybe the wrong kind of way to test these systems. And I wrote about this in my blog. Other people have written about how these are the wrong answer to the wrong question. So how do we test these systems? Well, another thing is we can try to kind of get at the heart of understanding, give them tasks requiring abstraction and reasoning. And some people have hypothesized that even though they're trained just to predict the next word in a text, that they've somehow gotten these emergent abilities to do abstraction and reasoning. Ilya Sutskever, the co-founder of OpenAI, makes a very ambitious claim that he says that when we train neural networks to predict the next word in text, it's learning what he calls a world model. It's learning about people, the human condition, their hopes, dreams, and motivations. The neural network learns a compressed, abstract, usable representation of that. So that's a big claim. What's the evidence for it? Well, you can test these systems on these tasks that require such abstraction, but then the question is, how real are the abstractions that they create? So other people, like Jan LeCun, who ironically gets quoted in our talks as like the AI skeptic, which is a little strange, but he says, well, are they really doing this thing that Ilya Sutskever proposed, or are they doing something more like what people have called approximate retrieval, which is sort of looking at similar patterns in the training data and using that to solve a problem? And he says autoregressive LLMs are largely on the retrieval side. And this was taken even further by Kamapati, an AI researcher at Arizona State, who said that emergent abilities is the preferred euphemism for what your LLM does when saying approximate retrieval sounds too unsexy. So he's pushing it even further. And we can ask the system to do some kind of like spatial reasoning tasks. So I asked ChatGPT-4 to draw a picture of a blue box stacked on top of a red box, which is stacked on top of a green box. So blue box on top of red box on top of green box. And here's what it gives me. So it gives me the red box, a blue box on top of a green box on top of a red box, which is not what I asked for. But if I ask it what color is the box on the bottom, it will tell me the box on the bottom is green. Okay, so that doesn't seem too great. I can say, please draw a fruit bowl with no bananas. Here's its solution, and it says, here's a picture of a fruit bowl filled with various fruits, but with no bananas included. Okay, so this is, these kinds of being able to reason about negation is a bit of a challenge. And taken even further, there's been a number of papers about reasoning and in large language models that show that if you, to give it a reasoning problem that is similar to problems in its training data, it will often do very well. You can see these bars up here are the accuracy on certain reasoning tasks. But if you change the reasoning task to require the same abstract reasoning ability, but with content that's quite different from the training data, it will do much worse. So here's one example of that on what's called code execution. So here, the task was to take a little snippet of code that is here in sort of the beige block in Python, and to execute it and show what the system would output. Okay? And here's the prompt. You're an expert programmer. You have to give it this pep talk of, as Yejin mentioned. What does the following snippet of code in Python print? And it gets that right. That's the blue bar up there. That's the accuracy on these snippets in Python. But then they changed it, and they said, let's just do what they called a counterfactual task. Instead of Python, we have this fictional programming language called ThonPy, which is identical, except instead of lists and arrays and things being zero indexed, which means that people, if you know programming, you know what that means, but it means that if you have a little list of things, the first element is indexed by 0, the second element is indexed by 1, and so on. If you ask it to change that to 1 indexing, simple change, now the system is no longer able to do very well. That's the reddish bar up there is the accuracy on those counterfactual tasks. So this group did this for a whole bunch of tasks and showed that GPT-4 was much worse on these so-called counterfactual versions of reasoning tasks. And this paper, which Yejin mentioned, Embers of Autoaggression, showed a very similar thing. These bars are showing different reasoning tasks, and the higher bar is the one that has the reasoning task with sort of what's likely to be common in the training data, and the smaller bars are the ones that are the accuracy on tasks, the same task except with content that's rarer in the training data. My group did a similar study. There was a paper published last year called Emergent Analogical Reasoning in Large Language Models that showed how GPT-3 and GPT-4 could do very well on certain analogy tasks. But we were able to show that if you do the same kind of counterfactual task, that is, change the task so that it's less likely to be in the training data, and this was our paper, this was with my collaborator Martha Lewis, if you take the original task, and here the blue dots are studies on human accuracy, and the other ones are different GPT models, you can see that humans are able to perform well across the different counterfactual tasks, but the performance of the GPT models decreases significantly from the original task. So the take-home message here is that large language models are better, often dramatically, at solving reasoning tasks that are similar to the content seen in training data, and worse when the content is not similar to the training data, which raises the question of whether they're actually performing abstract reasoning or they're doing some kind of pattern matching with examples in the training data. Well, my assertion is that these kinds of failures of understanding are due to a lack of human-like concepts and abstractions. And the question is, how can we get machines to learn human-like concepts and abstractions rather than these kinds of statistical associations or pattern matching abilities, and to make analogies? Well, human concepts have certain kinds of properties. We think of them as mental models of categories, of situations, events, and even one's own self is a concept. So just consider a simple concept, the concept of something being on top of something else, okay? Well, we know that concepts are compositional. If we understand one thing being on top of another, we understand another thing being on top of that thing. You know, we can understand and generalize our notion of on top of. If we understand a cat on top of a television, we also understand a television on top of a cat. And I was actually, the first image here, cat on top of television, I think I was able to generate a cat on top of a television with the text-to-image program DALL-E, but not a television on top of a cat. Concepts have causal structure. So one criticism of large language models is that they use statistical correlations. They don't have any notion of causality. Concepts enable predictions. They enable the kind of abstract reasoning that humans often can do that sometimes large language models lack, and common sense. So, you know, babies learn very early on that sort of the causal notion of concepts like being on top of something and what happens if you, say, push on a pile of blocks that are on top of each other. It helps knowing what on top of means includes knowing how to get on top of something, so children can figure that out pretty easily. And, you know, topological notions like your shoes go on top of your socks, so you have to put your socks on first. So these are very basic ideas that we humans learn by actually living and interacting in the world. But also concepts can be abstracted to new situations via analogy and metaphor sometimes. So here's just, you know, some ideas of how on top of can be abstracted. So, you know, I can think of on top of not just spatially, but metaphorically. I can be on top of my game, or, you know, temporally at the top of the hour, or at the top of one's voice, or on top of a social hierarchy. So we take our basic concepts, our spatial and physical notions, and we abstract them. Lawrence Barsalou, a well-known cognitive scientist, wrote that a concept is a competence or disposition for generating infinite conceptualizations of a category. So if you think of the category of being on top of, and your concept is your ability, it's a generative ability to generate different variations of that, and infinite possible variations of that. And I think that's right. And Lakoff Lakoff and his collaborators have talked quite a lot about how abstract concepts are learned via metaphors involving sort of basic core concepts. You know, like social interaction is, we think of it metaphorically in terms of, say, physical temperature, like she gave me a warm greeting. Or status is thought of in terms of physical location. She's 2 rungs above me on the corporate ladder. Okay. Barsalou et al. Also proposes that concepts are grounded in mental simulations of physical situations. This is another hypothesis about concepts, that the way we use concepts is we actually simulate them. And this is also, you know, recent work that people, for instance, Josh Tenenbaum and his collaborators think of the mind as a kind of simulation machine, sort of akin to a video game physics engine. So in my own work, I've been interested in how to build up concepts, how humans build up concepts, how machines could build up concepts. And I find the work of Elizabeth Spelke inspiring here, where her view is that all concept learning builds on innate systems of core knowledge that we're born with or we learn very early on. For instance, that the world is divided into objects, something that all babies can seem to know, that we know about concepts of numerosity, like something's greater than something else, or basic geometry and topology, like something's on top of something else, or something's inside something else, or surrounding. And she also said that we have innate knowledge of the difference between inanimate objects that don't have any agency and objects that are agents that have goal-directed behavior. So that's sort of the core knowledge hypothesis. And that inspired Francois Chollet, a Google researcher, to develop an evaluation set of benchmarks for sort of abstraction and reasoning abilities using core concepts. So he called this the abstraction and reasoning corpus. And here's an example of a challenge little puzzle in that corpus. So you have here, I give you 3 demonstrations of transformation between one grid and another. So, the top one, the leftmost grid is transformed into the right grid, and so on. And there's some underlying abstraction behind all the transformations. So you could probably see very easily what you're supposed to do to the test input to transform it in the same way. There's some notion of geometry here. That's an object is sort of shooting out a ray or light or something that goes to the boundary. And we know the direction it should go in because of the way the object is shaped. Here's another example of a task. So this one is sort of about shape invariance, where you color shapes, different classes of shapes, different colors, and it doesn't matter how they're rotated or translated or the size. Okay, and so Chollet created 1,000 of these, what he called tasks, that all sort of tried to incorporate these kind of core knowledge systems. He published 800 of them and held out 200 of them as a hidden test set. He then put up this challenge on the Kaggle website. Kaggle's a platform for machine learning challenges. People can submit their programs and they can earn money, like $20,000 here. In the end, there were 900 teams who submitted their programs to solve this abstraction and reasoning corpus that were then tested on the hidden test data. And the winning program got 20% accuracy, okay, which is not that high. Each program was given 3 guesses per task. An ensemble of the top 2 programs got about 31% accuracy, still not very high. And there's a new competition. This was last year's competition. But you now can, if you want to submit programs to do this task, you can make money. You can get 1,000 Swiss francs per percentage point above 31%. So go at it. My group got really obsessed by this ARC challenge, but we really felt that there were a couple problems with it, that it was too hard for humans. Some of the problems were actually quite complex. And it didn't systematically test understanding of these core concepts. So what we did is we created many new tasks, new variations, but each set of tasks was centered to be variations around a particular concept. So this gets back to what Yejin mentioned, that you can't just test on one example and then assume that the program understands the whole, everything that example sort of stands for. You have to test on many variations. And so we had 16 different groups of concepts that dealt with these very basic spatial and semantic ideas, like center, inside, outside, same, different, and so on. And for each group, we had 30 different tasks. These were my collaborators working on this project. We have a couple of papers out. So I'll give you some examples. So here's some examples from the top and bottom group. So you can probably see, we tried to make them as easy as possible for humans. And you can see here that the task, the rule is, remove the bottom object. And we tested humans using the prolific crowdsourcing platform. And we tested the winning program of the Kaggle competition and GPT-4 on these. And we tested GPT-4 in both the sort of a text-only version, where we just gave a text version and pixel values of these grids, and we also tested the visual version just by giving the picture. And these are results from the text-only version, which surprisingly did better than the vision version. But everybody got this right. 100% of humans got this right. Okay, but so does that mean that everybody understands top versus bottom equally? Well, we have to test some more. So here's another variation on that. So here you can probably see, color the top row of the object red. Everybody got that right again. Here's another variation. Remove the top and bottom objects. Well, humans, 100% still, doesn't seem that harder, but the programs didn't get that right. And so there's some kind of difference between the understanding of humans and the understanding of these programs. And we did this also for sameness and difference. So here's like, keep the objects that have the same shape. And humans, 100%, GPT-4 incorrect. Another one where same task, but you have some distraction, some boundary, some surrounding pixel colors. Humans 100%, and so on. And in general, here our results. You can look at the bottom row for the sort of bottom line here. Humans got about 91% of all of these problems correct. And if you've ever dealt with one of these crowdsourcing sort of human doing psychology tests on humans with these, 91 is like 100%. It's very noisy. Some people aren't even trying. And then the Kaggle program, which was written to solve ARC problems, did better than 20% here, because our problems are much easier. It got 51%. GPT-4, the best thing we got out of it was 33%. So to conclude, can AI understand the world? That was my question. Well, I think in principle, yes. There's no reason why we couldn't build AI systems in principle that could understand the world the way we do. Current AI is amazing, but it still has many failures of understanding, making it untrustworthy. And to understand the world in a human-like way, we'll need AI systems to have the same kind of core knowledge and resulting concepts that we have, that are mental models built up via composition, analogy, metaphor, and causal structure. And the big question, I think, is that do we think that AI systems, through language alone or through video and huge amounts of image and video and audio and so on data, can achieve this? Or do we need some kind of embodiment, like babies have, and active interaction in the real world? And I think the answer is we don't know. There's a lot of different opinions on this, but I tend to believe that without embodiment and active interaction, it's going to be very difficult to get to something like human level understanding. Thank you.
Okay, we have time for questions before we head for lunch. I wanted to make one thing clear. Earlier, I attributed the stochastic parrots paper to Melanie Mitchell. I was actually illustrating the AI phenomenon of hallucination. So I didn't actually make a hugely embarrassing error. It was just to be clear. Okay, the microphone is going around. Okay, Joyce is right here. She can start us off.
Great, thank you. Thank you, Melanie, for fascinating talk. So I actually have a puzzle, okay? I don't know myself. I really don't know the answer because there are a lot of work out there looking at like use ChatGPT. We're very fascinated about its ability. But then these models change over time, like Yejin showed in her presentation. Today and tomorrow might not be the same. So then, as I was working with my students, we're also kind of puzzled by, what kind of conclusions we can draw by using these large models. Like last year, there's a paper showing that only within 3 months, a bunch of benchmark tasks, they have sharp differences. So these are very complex, highly complex models. So I want to hear your thoughts on, share with us some of the thoughts on how to use these black box models to generate or reproducible results.
Yeah, I think that you can't use black box models like GPT-4 or something to generate reproducible results because it's a moving target. And this is why there's, the scientific community is trying to, is so supportive of sort of open source models, which previously haven't been at the same level as things like GPT-4, but very quickly are catching up. And I think they have to be open source not only in the weights of the neural network, but also in the training data that's used, because that's what we need to really understand what the true capabilities are. So I think scientists are getting frustrated with the commercial closed models, but we'll see a shift to people really working with open source models.
Thank you very much for your talk. And in your talk, you have mentioned that we should have distinguish between the so-called pattern matching and abstract reasoning. And I'm very curious about your perspective on what's the core difference between these two, because some version of the early AI systems, such as the structure mapping engine, they're basically also doing some part of the pattern matching. So what's the principal difference between these two methods?
Yeah, I mean, that's a great question. I don't think we have a totally agreed upon definition of abstract reasoning, but it's certainly something that is an ability to sort of apply a reasoning process to any new kind of content of a question. And so like Yejin showed that multiplication with GPT models is, it can get better with more training and so on, but it's not perfect. Whereas a calculator is perfect, right? A calculator is not going to be 99% right. It's just right because it's using an algorithm that, applies to any problem. And I think I'm not saying that humans necessarily are able to reason in that way, at least not without sort of a lot of work. And, but that's kind of the goal, is something much more, content independent.
Hi, thank you for your great talk, and I see you're making the point that we want to kind of learn concepts, and that's kind of the core of intelligence. And as humans, we use language to abstract concepts from the world, and language models are currently working pretty well. And maybe that, because of this abstraction, that's making it to work this well. And also in the language domain, in context learning, the language models can do analogies to figure out what are the relationships between the example query and answers, and try to give a answer to the current query. However, your examples are mainly based on the vision domain, which is not easily composable. And my question is, do you think now the problem becomes to we just have to align existing knowledge in the large language models to the vision modality, or you think there's like more we need to do beyond that?
Okay, that's a complicated question, but when you say we just have to align language to the vision modality, that word "just" is doing a lot of work. And people have still, I mean, this is the thing, these systems like, you know, GPT-4 have been trained on huge amounts of vision and tried to align it to language, and it still has many failures in that. So I don't think it's an easy thing to do. Again, you know, yes, these systems can make analogies for sure, and they're amazing, but sometimes they can't because, and the question is that because they really aren't making analogies the way that we do, or are they, you know, are they more dependent on sort of what's in their training data versus some more abstract ability? And that, I think, is not totally answered.
Final question.
Yes, as a hardware person, I'm fascinated by your last bullet point here. My question is, if OpenAI, Anthropic, one of these companies developed an AI, something with embodiment, active interaction in the real world, would you host it in your house to let it get data?
I would, you know, but I would be careful with it, right? Just like I'd be careful with my child filling up, you know, loading the dishwasher or something. You don't want to, you want to be careful with these things being autonomous. But as Yejin said, Moravec's paradox has shown us that physical intelligence, if you will, is much more difficult than sort of language-based intelligence. And that's why robotics seems to be still quite far from anything like, you know, AGI in the physical world, whereas these chatbots seem much more capable.
Sorry. Really two questions here. The first one is a more, I guess, practical question. Obviously, a real understanding will be great for robustness and interpretability, but I don't think we have obvious evidence yet why we might want to have real understanding just for benchmarking reasons. So I guess the first question is, why do you think we should push for this kind of real understanding? And the second question is, read a book recently by Marcus and Davis, and they're also talking about having real cognitive models, and they advocate for a return to a more classical AI and encoding those models more explicitly. And I think you're quite skeptical of these emergent properties. So what do you think about their approach back to classical AI?
Yeah, so you had two questions. One was, why do we care about sort of true understanding? And you know, I'm not going to say there is like one true understanding, but if we want to have these systems interact with us and work with us in the human world, like drive us around in cars, we do want them to understand the world the way we do. That we want them to understand, you know, what a stop sign is versus a stop sign in an ad. And that's the way that we're going to be able to trust these systems and make them reliable. As for, you know, there's kind of this new fad of what's been called neurosymbolic AI, which is trying to unite the neural net approaches with more symbolic classical AI systems. You know, to some extent that's already been done to in quite a few real world applications, and it's useful. But I think ultimately, you know, it was it's hard to integrate these kinds of approaches, and it's not clear that symbolic-like approaches are going to be robust enough to solve these kinds of problems that we're talking about. But you know, it's kind of it's a research question, and I think we'll see a lot of results from that community.
So again, lunch is across the way, and we'll reconvene in 90 minutes. Let's give a huge hand to Melanie Mitchell. Hi, folks. Technical difficulties are resolved, and the afternoon program is underway. Again, I'm Chandra Sripada, director of the Weinberg Institute for Cognitive Science, and we had terrific talks this morning, and we're going to continue the momentum with Paul Smolensky, who is Krieger-Eisenhower Professor of Cognitive Science at Johns Hopkins University and a partner researcher in the Micosoft Deep Learning Group at Redmond, Washington. His work focuses on the integration of symbolic and neural network computation for modeling reasoning and grammar in the human mind-brain. His work led to major developments in the field, including harmony networks, also known as restricted Boltzmann machines, tensor product representations, optimality theory, and harmonic grammars. Notably, he was a founding member of the Parallel Distributed Processing Research Group at UC San Diego, and that was the group that's famous for the PDP books that were a centerpiece of the first wave of neural network models. Professor Smolensky has for decades been at the forefront in responding to doubters and critics who say that neural network models can't do this or that type of processing. Today, he continues this pattern of responding against the claim that neural networks can't engage in something called compositional processing. He does that in his talk titled "The Current Compositionality Crisis in Cognitive Science." Please join me in giving a huge hand to Professor Paul Smolensky. Quick reminder of the afternoon that I didn't tell you the schedule. We'll do this talk followed by another. We'll have a wonderful panel discussion with audience participation, and then break for a reception. Everyone's invited. Professor Smolensky.
Do you want your computer, Melanie? Or just oh, okay. Well, thank you for that lovely introduction, Chandra, and for the invitation to be at this exciting event. It's been great to hear about the developments in cognitive science here at Michigan, given that there's so much talent that needs to really be Is that better? No? How about that? And you thought the technical difficulties were over. Okay. I'm going to be presenting work for the first time. It's a totally new talk, and I don't know how it's going to go. So excuse me if I stumble at places. I'll probably get lost in my animations, but with your forbearance, we'll get through it. This is joint work with Roland Fernandez and Junfeng Gao at Microsoft Research, plus a lot of other stuff that I'll bring in as well. So I'm going to talk about the current compositionality crisis in cognitive science, start with an in-depth case study, and then bump up to a more general analysis of the issues in compositionality in neural networks, and then end with discussions of going from the theory we've developed to practice. So the current compositionality crisis for me is this. I believe that compositionality empowers human intelligence. I believe that cognitive science has got tons of evidence in favor of that claim. To achieve a goal, we break it into sub-goals and then break those into sub-sub-goals. To interpret a scene, we break it into sub-scenes. To interpret an utterance, we break it into sub-utterances, which we break into sub-utterances. We encode nearly everything as wholes built of smaller parts. That allows us to learn how to deal with the small parts and how to combine them, and hence how to deal with infinitely many novel combinations. Previous AI systems built with symbolic computing are inherently compositional. For example, using grammar rules in linguistic theory and for natural language processing systems in applications. The symbolic computational environment gives us the ability to write these rules that say a sentence is a noun phrase followed by a verb phrase, and use those to generate hierarchical tree representations for sentences and all sorts of other aspects of cognitive representations. But the current language models blow the symbolic NLP systems completely out of the water, even though those systems have compositionality at their core. And a lot of people question whether these language models know what they're talking about, whether they have understanding, and I think that those are very key questions, but I want to point out that the syntax of what they generate is astonishingly good. And anybody who's taken a course in syntax has to appreciate what that means. We always thought you had to have 1,000 rules like that in your head, and all the symbolic processing mechanisms to take advantage of them to generate syntactic sentences of English. And these neural nets just do it, just nail it. And so why are they better than the symbolic natural language processing systems that they've replaced? Is it because they're more compositional, given how important compositionality is to language, as well as the rest of cognition? And the answer there seems to be no, that there remain pervasive challenges of compositionality for neural networks and language models in particular. That's not the reason. So before we can talk about what the reasons are, I need to talk a bit about what these current language models look like. They are neural networks. They're a type of neural network called a transformer. And I'm sorry this is too small, but I'm going to read what's on the screen if you can't. So transformers are a kind of neural network in which a sequence of words is given as input, and the model needs to continue that text by generating new words. At each layer of this multi-layer network, for each word, there is a newly computed activation pattern or activation vector that encodes that word in the context of the rest of the text. Each word's encoding contains a key activation vector and a value activation vector. To compute a word's encoding at a given layer, say, for example, the word she, the word she issues a query, which is encoded as an activation pattern, as everything must be in a neural network. And this query that this word has issued is compared to the keys of all the other words at the layer. To the degree that the key for some other word, say Michelle, matches the query, to that extent, its value vector is passed back to she, and this is used to create the new encoding for she in this context, at this level. The encoding of she, therefore, acquires information about Michelle, who it in fact refers to. All done by spreading activation among neurons through numerically weighted connections of the sort that you saw in Melanie's talk. So what I'll refer to occasionally as the classical argument is that neural networks are just plain ill-suited for compositionality. Fodor and Polishin's paper, the most frequently cited one here from 1988, Connectionism in Cognitive Architecture, Critical Analysis and Cognition. They took up a question like, what would you be able to do in the way of compositional representations in a neural network? Instead of a tree, like sentence, which consists of a noun phrase followed by a verb phrase, you could have a single unit that stands for that. But that's not compositional. There are no parts to it. You could have 3 units, one for the S, one for the NP, and one for the VP. But how are you going to express the fact that the NP precedes the VP and that the NP is part of the S? So they argued that neural networks do not provide a natural basis for compositional representations and ipso facto compositional processing. Now, as I will say later at the end, I'll give a spoiler. This is a hoax, but we're going to play along with it for now, as the rest of the field has done for 40 years. Okay, So the crisis is, compositionality is important for intelligence. Symbolic AI systems have perfect compositionality built in. Neural networks struggle with compositionality. So why are neural networks outperforming symbolic AI systems all over the place, including generating syntactically valid English? So the purpose of the talk is to show how transformer neural networks can do sophisticated compositional symbolic computing. In the end, we'll bring this in service of the neurocompositionality hypothesis, which is that the right type of neural network can do what symbolic computing can do, but better. It gets continuous generalization from having non-discrete parts and can do what was so hard to do in previous generations of compositionally based symbolic computing. They have a very powerful route to learning these representations and how to use them. Okay, so I want to start with an in-depth case study to ground the more general analysis to come. One of the things that language models can do through what's called in-context learning, and I'll explain what that means in just a second, is deal with things like this rule of inference. This is going to be where we give this rule of inference as part of our input to the network, not training, but the input at performance time. We're going to say that x implies y is equivalent to y or not x. And here's an example of a prompt that does this. So it says Q, colon, x implies y, A, y or not x. The prompt gives the rule of inference stated in terms of variables x and y in the form of a question-answer example shown here in green. You can't see my cursor here, yes. That's too bad. Okay. The green portion of this prompt that would be typed in to the language model's input buffer gives the rule of inference stated in terms of variables x and y, and then gives a Q that is supposed to generate a continuation. It says Q, U and V implies Z, A. So what is the answer if the question is U and V implies Z? The answer is supposed to be Z or not U and V. And Text DaVinci 3 actually gets this right, okay? It's called in-context learning because it's sort of learning to use this rule in the context of the input rather than during training, okay? So I'll be referring to in-context learning, or ICL, throughout the talk. But that's all it means. I think it's a misnomer altogether. It's not learning at all. It's pattern recognition and pattern template filling, in this kind of case, at least. That's the kind of we'll study. All right, so we'll see that the model needs to recognize the overall question-answer structure of this prompt, recognize x and y as the variable slots in a general template for some question-answer pair, needs to recognize in the second string, the Q, that U and V is a new value for x and Z is a new value for y, and it needs to know that it needs to plug those new values into what the template provided as the answer before to give Z or not U and V. There's a fair amount of sophisticated symbol processing involved here, actually, and these models do decently well. And our question is, what neural mechanisms internal to the transformer networks allow them to do that kind of symbol processing? I need to point out that while Text DaVinci 3 succeeds here, the success is not very robust. So if we just omit the colons following the Q and the A, it gives us not, no, this is not logically valid as its response. GPT-3 also fails completely if we omit those colons, or even with the colons, it fails. So most attention has been directed towards these failures. You know, engineers want systems that work. This is a failure. What do we do to fix it? Our question here is entirely different. I want to know how they succeed when they succeed. How is it possible for it to get that right? Given that we've been told for years how this kind of processing is well beyond what we should expect neural networks to be able to do. So how are successes like this and the high syntactic accuracy of ChatGPT's English possible? And we seek a mechanistic explanation. Now, this is notoriously difficult, figuring out what's going on in these large models. So we'll follow Richard Feynman's maxim, despite the fact that Yejin was making fun of it. We're going to do it anyway. Richard Feynman's maxim, what I cannot build, I do not understand. Okay, the contrapositive is, if I can build it, I understand it. Now, one can question this maxim, but we're just going to follow it. Okay? What we're going to do is hand construct a transformer to do this task. The knowledge will be installed by us via programming, rather than by some magical extraction process from statistics of data in learning. Okay, so we're going to dive deeply into this particular case. So the model is given this prompt in blue text, asked to generate the response in orange text, here, Z or not, U and V. In this templatic text generation task, the text string has two portions, an example and a queued completion for generating new text. We need to recognize the template exemplified by the given example and repeat it in the queue. It can be represented by this constituent tree. I will spell it out in larger fonts shortly. The two top-level portions of the prompt are the example, which we labeled by the label X, and the continuation, C. The example has two regions internal to it, a Q region, a question region, and an answer region. And each of these consists of a sequence of fields where different symbolic elements get inserted. And the QR sequence is, that is to say, the question region, has an FQ, which just holds the Q, and then F1, F2, F3 as its subsequent three fields. The A region's fields are first FA, holding the A, then F3. And we recognize that it's a repeat of F3 because the same symbol appears in its place as in the question part. So we recognize it as a repetition of field 3. And then there's a new field type, F4, that contains or not. And then there's a repetition of the field F1 because, oops, sorry, I'm tripping over my animations earlier than I expected. So the all right, so what is in the completion part here? What does it look like? It repeats the syntactic structure of the example. So the Q region has the same sequence of fields is in its question region as does the example. FQ, F1, F2, F3. But the symbols filling some of those fields have changed now in the continuation. FQ and F2 serve as delimiters. They have the same content in the example and in the queued continuation. And they delimit the variable portions, which are now to be inferred as what happens between the delimiters. F1 was X, but is now U and V. F3 was Y, but now is Z. So the task is to fill in the template using the material given in the queue that we just went through. The new A region is the continuation that the model needs to generate as its output. F3 is the same sequence of fields as it was in the example, but now F3 has changed, and F3 has changed to the new value. It appears in blue there, Z, and F1 has changed from the simple symbol X to the expression U and V. Okay, so how do we generate these new symbols? First, we have to compute the parse structure of the prompt. And we'll talk about how that's done shortly. The parse reflects a set of constraints on the prompt that define the version of templatic generation that we are studying. We begin to generate the new text by starting from the final symbol of the prompt, A. We identify its field, FA, and then find the same field in the example. That's step 1. We next identify the example's subsequent field, which is F3, that's step 2. We then find the field, that field, F3, back in the queue to get its new symbolic value, Z. And finally, we copy that value into, to the end of the prompt to generate the new symbol, Z. All that has to be done just to get that first symbol generated. Okay, so to review what I just went through, we see from the example that an A region consists of a sequence of fields, FA, F3, F4, F1, F5. Therefore, the continuation follows the final A with the next field that was given in the example, namely F3. We use these 4 steps that I just went through over and over again each time we need to start to generate the symbols that fill the next field. And this operation is called next field. Another operation, a continue field, is needed to fill in all the other symbols within a field after the field has been started. So once we start this field F1 with this left parenthesis, we then have to switch and use continue field to fill in the U and V right parenthesis that was all part of the same string, which is the value of that field. Next field and continue field are closely related to the notion of induction head that you may be familiar with. It was introduced by Anthropic in their mechanistic analysis of in-context learning and transformers. And we will come back to that. Okay, I'm going to simplify this structure slightly before we go any further. We'll just relabel the parts of the example as XQ and XA and drop the X itself. Same thing for the continuation. We'll change the question and answer field names to CQ and CA, and drop explicit discussion of the top-level constituents, which don't play a role in our algorithm. Now, we want to express the operation that we just went through, next field, those 4 steps, as a program running on an abstract machine. We call this machine the PSM. Eventually, you'll see it stands for production system machine. Here's how the parts of the the input looks in the PSM. Okay, in the PSM, the computational state of each symbol in the prompt and the continuation is a discrete variable value structure. The first symbol's computational state is this structure shown here. It's the variable S filled with the value Q, the variable R assigned the value XQ, and so on. And this is all true of position 0, as Melanie explained. We start counting with 0. Position, this is the state of the representation in this machine at the first position of the prompt, tells you what the symbol is, what the fields are, and other things like what type of it is, whether it's a delimiter D or a variable constituent C. Okay, and so some of these variables, crucially, are structural variables that contain the structure of the parse. And so we see here that you know, the initial span, which was in this tree structure shown as an XQ that spans the whole initial part of the string, now is represented by a bunch of XQs that tell you that the region in which is contained the 0th, 1st, 2nd, 3rd symbol, the region is the XQ for all of them. They all fall into that first constituent XQ. And similarly for CQ, which is the question part of the Any luck? Any luck? No luck for a pointer. Okay. Do you have a laser pointer? It's become ridiculous that I can't point at things with my cursor. Well, I'm not communicating with it. I'm just trying to. You should try to use the laser. Might not see that. Did I fail to turn it on? Here. Okay. Okay, there it is. All right, so the CQ, the fact that the tree structure looks the way it does is encoded in this machine by saying that the region assigned to all these symbols here is the same, CQ, as opposed to this one, which is X. Now, okay, so, and the internal sequence of fields within XQ is shown as the values of the variable called field here. So that's where this information is, FQ, F1, F2, F3. And this method for encoding hierarchical structure in a transformer-like space of representations was proposed in Jeff Hinton's GLOM architecture. Okay, so I'll just quickly mention that it's very convenient for what follows to define for every state variable x the associated variable previous x, or x star, defined everywhere by the value of x star at position m is the same as the value of x at m minus 1. Okay, so we can get information about what's at m and what's right before it from the variables sitting at m. We can only attend to one place ultimately in our transformer, and that's why we need to do that. Okay, so here's the new primitive operation in our programming language. The currently final symbol A is in a position that we'll always call capital N. To generate the next symbol, which is Z, in position N plus 1, we will update the variable called next symbol at N to have the value Z. So that's what we want to do to start the process of generating our next symbol. So how do we do that? To do this, we're going to combine operations 1 and 2. Oops. Sorry. We're going to combine 1 and 2. That's going to be done by finding a position, small n, which has the property that it's in the region XA because in step 1 we have to jump over to the example region, the answer part of the example region, XA. So we're going to find a position little n, which has for its region variable XA, so something over here, and which has as its preceding field our current field. So what we have at the end of our prompt now is something in the field FA. We need to know what to generate next by going back and saying, okay, what follows field FA in the example? So we go back and we find field FA here. That's what this first step does. And we look at the next field, F2. F3. Okay, so that's combined into one operation now. And we find the next field's value, F2. So now we know we need to generate next a symbol for the field F2. So we assign this field value to a variable at position n that we're trying to update. It's a temporary variable called f prime. We've recorded in there the fact that what we want to do next is generate something for an F3 field. And all of this is part of an operation which will be contained in something called next field 1. And then steps 3 and 4 are used to find another position by jumping back to find the new value. We now know we want to generate an F3, but we'd have to find out what is the value of F3 now. Before it was Y, but now F3 has changed to Z. So we need to jump back. So we need to find a new position, little n, which is in the queued context region instead of in the example region, but which has the right field value. And then we find the symbol in that field, what field's value, field F3 is the symbol Z. And so we take that symbol and we assign it to the next symbol variable of this position. And now we're done. What will happen next is that when the next symbol is generated, it'll just take this next symbol value Z and spit it out. Okay, so we can express these two operations here, next field 1 and next field 2, as production systems, as productions in a production system. And so the condition for the first production, next field 1, is that little n and big N are two positions that must satisfy that the region of little n has to be XA, the value of the field at n, capital N has to match the previous value of the field at little n. All the stuff that was written over here is the condition of the production. And the action of the production is to assign this value to that variable. And this is the same kind of structure for the second part of the operations. So what needs to happen is that these two productions need to operate in order to find the right information from the example and the queue, assemble it, and spit it out as the continuation. So these are two productions that are part of 7 productions, which collectively solve this problem of generating all of the continuation text in response to our query. So these are what all 7 look like. And I'll just point out that the task we're looking at really does involve a lot of serious use of compositional symbolic structure. And here's a whole list of things. I decided not to go through them. All the different aspects that are crucial to symbolic representations and processing for compositionality are present in this problem, with the exception of recursion, which is an important exception. So what we just saw was that the productions for generating symbols, gen, crucially rely on the parse structure. And so where does that come from? Well, it turns out that the same type of productions used to generate the continuation can be used to compute the parse. But we need 22 productions to do it, or at least the way that we thought to do it requires 22 productions. And I'll just illustrate a little bit with CQ here. Actually, I'm running a little bit behind, so maybe I won't. I will just flip through this quickly because you just need to know that the same kind of productions can be used to do the parsing. That is to say, to assign the values to the structure variables, to figure out what the fields are for each symbol, what the regions are. All that stuff, the parsing process, is handled by productions that assign values to these structural variables, field, region, and so on. So this was an example of one of the steps in that parsing process handled by production F8, which is illustrated here. The little n and big N have to satisfy all of those conditions, and the action is to assign a certain value to a certain variable. And it's a structural variable, in this case, the field variable. This is the most complicated production in the whole program, actually. And once the first symbol in this field has been assigned by the production we just looked at, I just showed you, once this F1 is in place, then we propagate with a different production the F1 forward to fill out the whole constituent until you bump into the next field, which is a delimiter field that tells you that this field F1 has ended. And the way we know that that is the end of this field, that there's a delimiter region here, which is this symbol here, compound symbol. We know that because we previously, in an earlier step of parsing, assigned these values F2 and D here, saying it's a delimiter, by noticing that the symbols that appear here match the symbols that appear here. And that's why it's the same field, and that's why it's a delimiter field, because only delimiters repeat in that way. The way we've formally defined what the task is that the model needs to compute here is what justifies a lot of the assumptions that go into the parsing process and represented as productions. Okay, and so these are the parsing productions, and I will just point out that this is a very interpretable kind of analysis because we have a gloss here that tells us in English what each of these productions is doing. Okay, we can understand every step of the way that way. There's something innovative here that goes beyond what's part of standard transformers, and which will lead to innovation in our ultimate transformer for implementing this, is that this production system allows us to have blocks that are repeated until no further change in variables occurs. And that's important for propagating that symbol. We keep propagating it until we hit the next delimiter that says stop. And so these kind of repeated operations, these loops, are an architectural feature of this language that's important. Okay, so that was this case study I wanted to put in your mind to use to hang this more general analysis from. So what we're going to do is follow the advice of Jessica Hamrick and Shakir Mohammed, who said, you know, there are these things called Mars levels. We should use them when we talk about machine learning systems. Good idea. So let's do it. So I'm going to present our work, the transformer production framework, through Mars levels. And the top level is the functional level. That's where we formally define the template or templatic generation task. And below that is the more abstract of the two algorithmic levels, which uses the production system language that we just saw to describe computation in our production system machine. Below that is another algorithmic level, which is less abstract. It's called, it describes a machine called the QKV machine, query key value machine, because we're working our way to a transformer implementation. So we have a compiler that takes our production system language program that we just saw. There are 29 productions altogether, and compiles them into instructions for this lower level machine, the QKV machine. And then finally, we have the implementation level. And we have a compiler that takes the instructions for the QKV machine and turns that into numerical weights, which can be plugged into a simulator for a certain type of transformer that we've developed called the discrete attention-only transformer, or DAT. Okay, so notice that this is a framework for hand programming transformer weights, not for learning them from examples. Okay, so the templatic generation task has been cached into a data set that is generated from sampling from the grammar for this task. The data set is organized into 1, 2, and 3 shot prompts. So the input-output pairs have as their input an n shot prompt, which gives n examples of the template. And then a queue for continuation, which is used to generate another example. And the continued example that needs to be generated, the target output, is the paired output associated with this input. So here's an example that is a one-shot example. It has one example of the template. So I've parsed it with colors here to help us, but the machine doesn't have that advantage. So it has to figure out how to break this thing up. So it recognizes that the question consists of 2 variable fields. This white tiger fills the first one. That narrow zebra fills the second one. These are all randomly generated. And the answer is that narrow zebra, this white tiger. So the template says to swap these 2 arguments, and that you need to break the arguments up by recognizing that this exclamation mark delimiter separates the 2 in the question, and that in the output, that becomes a right parenthesis. These are randomly chosen delimiter symbols, and that this is attached to the end. And so this is one example that we give it in the input, the prompt, of what this particular template is. And then we give it the cued material, our tall, thin giraffe, his cool green car, and it needs to recognize that, okay, so in place of this white tiger, I should use our tall, thin giraffe, and that this replaces the green part of the example, and so the correct output, according to this answer here, is the green stuff followed by the blue stuff separated by a parenthesis. And every example in this data set is randomly generated from a grammar that produces these things with different symbols playing the roles of the variable, of the delimiters and so on, and different numbers of constituent parts. And all of that is randomly varying from example to example, except for the letters Q and A, which are fixed. So we have a grammar that generates these examples. And the only reason to mention this really is that the grammar incorporates some constraints that are important when we parse the input. We have to know about these constraints in order to recognize how to parse it. And so the first constraint says, no symbol can be repeated within the question, within the answer, or within the cue. Symbols can't be repeated, so that when we go to try to find the matching symbol, there isn't a possibility of ambiguity there. And there's another similar kind of constraint that's imposed on these examples. So this is the formal definition of the task that our computational system is supposed to solve. This is the functional level description. Can transformers actually learn to do this? First of all, we looked at pre-trained models, and just gave them these 1, 2, and 3-shot examples out of the, without changing the language model at all. No fine-tuning or anything, just out of the box. You can see that GPT-4 does extremely well, getting high 90s accuracy even with 1 example, and 100% with 3 examples. We also looked at whether a transformer trained from scratch on this data set, rather than taking a pre-trained model, it's been trained on the web. If we take an untrained model, train it on this sorry, what just happened here? Okay, yeah, I just pointed out that our program gets everything right. The algorithm is correct. And when we train from scratch, rather than using a language model, take a transformer with these various architectures and non-transformers as well, you can see that you get pretty good accuracy for the 2 at the bottom, which are both transformers, even with just 1-shot examples. So it's definitely the kind of thing that a transformer can learn. So when we're trying to develop theories to explain what it is that these transformers can do and what they can learn, this task that we're looking at now is a relevant one. And it's got the type of symbolic compositional properties that make it of interest to people who think that compositionality is really a problem that can't be solved by neural networks. Okay, so that was the functional level. Now we'll go down to the algorithmic level, but let's see. Given the time, I have to make some choices here. We've already talked about this level, actually, so there's no choice to be made here. We've talked about the production system language, which is the highest algorithmic level description of our computational system, the TPF. But the next level down involves a different kind of machine. And I'll just show you quickly, without belaboring it, that in this machine, we don't use productions to update the values of the variables. It's got the same kind of data structure here to represent the state, but we don't use productions to update the variables. Instead, at each position, we generate a query, a key, and a value. And those are symbolic structures, just like the input structure there was. They're in the same space. Okay, so just like this, we have a query, a key, and a value structure that appears in every position. And the state for the word at position, capital N, is updated by taking its query and finding another position where the query matches the key. And then the value where that matching key is found, the value structure there is sent back and used to update the state that we're updating capital N. I have to skip the explanation of really how it is that we compile the production you see here, next field 1, into a set of queries, keys, and values shown here. But the mapping is sufficiently straightforward that building the compiler is perfectly feasible. Okay, so each of those productions that you saw before here, can you see this thing? I can't. Each of these productions gets compiled into one of these QKV instruction sets. This tells us what the symbols and values need to be in the query, and the key, and the value, and each production corresponds to another level in this machine. And finally, I'll tell you about the implementation level and then switch out of the details to the more general kind of conclusions we want to draw. Okay, so the implementation level involves taking the kind of structure that we were just looking at here, which in this example is the key. The key for the layer of the transformer that implements production, this production, next field 1, has these variable value associations as its structure. And this shows how that gets implemented in the neural architecture. It's a very transparent, trivial thing that for each of the variables, we have a subspace of the vector space, and they're represented by these units here. And so all these units here collectively represent what value is being assigned to the variable little r. And the one that's turned on is the one that corresponds to the symbol xa. So this is saying that this variable has that value, and similarly for the other ones, these variables are not set. This is the state of the model's representation of the symbol in a given position as you're going up the transformer, and that has to be used to define a query, which is another structure of the same sort. We have a matrix here, which is a numerical matrix that takes this and converts it into the appropriate query, which has the same kind of form. And in addition to weights that define the queries, we have weights for the values and the keys. We have a simulator that allows you to see each stack is the representations of a different symbol, and there are 29 layers, so you can scroll up and down as you like, and you can indicate which variables you want to see the values of, and this tells you what the productions are that are being, the QKV instructions are, and the gloss in English of what is being accomplished at each of these layers. So I say Feynman vindicated because in this transformer, we understand exactly what every neuron and every connection contributes to producing the correct behavior, because we built it. And we understand how transformers can do serious symbol processing via in-context learning. In principle, they could be doing it this way. Now, a lot of people will want to know, well, what's happening in practice? That's fine. That's something you could have it in principle. But I want to point out that it was an in-principle argument we are responding to. We were told, in principle, neural networks cannot deal with compositional processing and representations. Okay, and so this is a way to produce a hypothesis for how these actual trained language models might be doing the in-context learning that they do. And so what we've learned is that there's a certain type of transformer that can encode a cell state as a vector embedded structure encoding the values of a set of symbolic state variables, employ the same structure for queries, keys, and values, encode in a cell state abstractions like the role of a symbol in the parse of the prompt via structural variables, encode an entire hierarchical parse structure in the state of a layer, use simple weight matrices to generate QKV vectors that implement symbolic productions. We can implement a higher level symbolic programming language for transformer computations this way. We can write and thereby implement programs which parse the prompt and generate language in a way that's sensitive to the parse structure of the prompt. This is the kind of thing that Fodor friends said we would never be able to get neural networks to do. Okay, and so from theory to practice in negative 13 seconds. Ready to go? Seatbelts firmly attached? Okay. Our trained transformers using something like our TPF algorithm. Anthropic's mechanistic analysis of ICL in language models identified induction heads, which basically say, as the symbol following X, generate that same type of symbol that previously followed X. Not very exciting, really. And that's exactly what our boring production continue field does. But the next field production, which we looked at, operates at a higher level of abstraction. It says, following the field F, generate the Q value of the same field that previously followed that field. Okay, so it's one level higher than the symbols following symbols. It's now fields following fields. are trained transformers using something like our algorithm? Well, in this interesting paper, they look at transformers that are trained to answer questions like this, or I guess some of them are trained to do this. And what they show, I'm going to have to jump to the punchline here. They don't phrase it this way, but what they're showing basically is that what they have found is that in their transformer, it's doing what we just described, really. It has a set of variables that are assigned values. So when you say J lives in Boston, then there's a structure that's used to represent J. The person's identity is J, the place is Boston. This is the first fact that we're given. And then there's another fact that K lives in California, that's fact 2. And the first production we need to answer the question, where does K live, is what fact talks about K? Okay, answer is, you apply the production, we'll end up getting it that it's 2. And then with that in hand, we then feed it to production 2, which says, okay, in fact 2, what is the place? And there we go back and we find the answer in this location here, namely California. Okay, so there's some evidence, indirect though it be, that transformers actually learn to do things this sort of way. All right, now we have, I've shown you this way of implementing it. This uses one-hot encodings for the variables and their values, but this is a special case of tensor product representations, which don't have to be one-hot. They don't have to just have a single unit for the value xa. They don't have to have just a single row for the variable r, okay? We know what tensor product representations look like that carry exactly the same information, and we know that exactly the same kind of production procedures can operate on those distributed, not one-hot representations. Therefore, we can ask the question, if we look at a trained model and look at its distributed representations, is it actually a distributed version of this? The hypothesis is that this is the content of its representation, and then we need to just figure out what distributed representations it uses for the variables and the values. And it turns out that we already developed software to do that. It's called the Discover technique, which has been used to find tensor product representation approximations to learn distributed representations in various types of networks, recurrent networks and transformers. Is there independent evidence that intelligence arises through production systems? Only about 60 years of amazing work in cognitive science. I invite you to talk to Rick Lewis and John Laird about it. So the neurocompositionality hypothesis is what all of this research is in service of. It was laid out in this paper in the AI magazine. And the claim is that human-level intelligence is enabled by having encodings of information that are simultaneously continuous and compositional. And we've even shown that in linguistic theory, you can make very important progress by using these kinds of continuous compositional, non-discrete representations as linguistic structures. And I encourage you to ask Eric Rosen in your linguistics department, who is a world leader in that. So the fact that the idea of being continuous as numerical vectors and compositional are incompatible is a hoax. We've known that tensor product representations combine those two just perfectly fine. And we've known it since 1988, thank you. We know that you can use these kinds of representations of continuous compositional structure to compute interesting families of recursive functions. You can prove that. Deep learning can learn to create and compositionally use tensor product representations. They enable rule-like processing where tasks are highly compositional to be combined with memory-based, similarity-based processing where they are not. And this is not a secret. I presented this in a debate with Fodor and Polishin at MIT in 1988. I invite you to look for a recording of it on YouTube if you're interested in archaeology. And that was part of a long-standing debate that I engaged in. These are the papers by Fodor and colleagues and me and colleagues in response. So this has been hashed out very thoroughly for a long time. But now we can ask the question, what kind of learning biases might be needed for deep learning to be able to acquire fully powerful continuous compositional representations? What kind of biases do they need to do a better job of learning these things? We know they can do it, we know the capability is there, but the learning has to find it. And so one possibility is that the biases that are suggested by the work that I just described, the DAT type transformer that allows us to solve this problem perfectly in an interpretable way, that the biases that would push a general purpose transformer in the direction of this machine might help. And those biases favor states that are tensor product representations and certain kind of weight matrices that basically just copy the values from one variable to another. So there are reasons to think that the DAT that we have, since we know it can do this task very well, might give hints as to how to get training in transformers to allow transformers to find the capabilities that we know they have. Thanks.
Thank you, Professor Smolensky, for a taste of cutting-edge research. No questions right now because we're a little bit over time. Let's take a 5-minute break and reconvene with Raphaël Millière, who will have a continuation or a dialogue with Melanie Mitchell's talk about understanding in large language models. So 5 minutes, which means 5:40, we'll reconvene. I'm sorry, 2:40. 5 minutes means 2:40.
Sorry about that, guys. I didn't have time to trim it down enough.
Well, you know, you managed to get it in 5 minutes over. So that's amazing. That is amazing. There's questions here for Professor Smolensky.
I'll bring this over to you so you're not reaching.
I think you need a lot of background to see what's going on there. Not that I'm following what's going on, but it's not incomprehensible. And production systems play a role. If you don't know production systems, then you're already,
Okay.
So I think there's a lot that needs to go in.
Would you just give me a demo of your last name?
Yeah, but you can pronounce it however you like.
I'll do my best. But I just wanted to double check.
Since 1988, it's hard to, there's a, if Fodor were here, let's not speak ill of his death. If he were here, he would bang his shoe and say, this is just a realization of classical representation. I'm not sure anything he said here has advanced the debate since 1988. I don't know. Well, Yeah. Well, I think you haven't seen maybe some stuff like that. Okay. Yeah.
Hello, everyone. We'll get started here again in just a moment, so please take your seats. A quick procedural note before I introduce our next speaker. After this talk, we will go into a panel discussion with all of our speakers. And from there, we will go into the poster session and the reception. So we encourage you to stick around for that. It's my pleasure to introduce our next speaker. Raphaël Millière is a lecturer, that is the Australian equivalent of assistant professor in philosophy at Macquarie University in Sydney, Australia. He completed his DPhil, that's the PhD, in philosophy at Oxford, and he was subsequently the Robert A. Burt Presidential Scholar in Society and Neuroscience at Columbia University. Professor Millière has emerged as a leader in using the tools of philosophy and cognitive science to understand the capacities and limitations of modern artificial neural networks based on deep learning architectures. His work addresses foundational questions about generative AI models. For example, the model question. What does it mean to say that generative AI models possess an internal model of the world? And the grounding question. Are representations in large language models appropriately grounded in the things out there in the world? Or are they just meaningless symbols inside the machine? Today, Professor Millière takes up another foundational question concerning our ability to understand the notoriously opaque inner workings of generative AI models. With a riff on the title of our earlier talk from Professor Mitchell, Professor Millière asks, can we understand large language models? Please join me in welcoming Professor Raphaël Millière.
Thank you. So when I was asked to pick a title for my talk, I thought I would playfully echo Melanie's. Is this better? Yeah. There we go. Okay. I thought I would playfully echo Melanie's title, not because I disagree with anything she said, but because as we've alluded to in other talks, in order to figure out what language models understand about language itself, about the world, we need to figure out how to understand these models themselves. So that's what I will focus on today. So here are some common claims that you might have heard about language models. On the one hand, you have people saying that these models only do next token prediction because that's how they're trained, so they're essentially glorified autocomplete algorithms, and we can't ascribe to them any more sophisticated capacities. In the vicinity of this kind of claim, we find the claim that there are stochastic parrots, we already alluded to as well, namely they just haphazardly regurgitate samples from the training data, and that's all they do. And then on the other end of the spectrum, we find claims such as this idea that language models exhibit sparks of general artificial intelligence. That was the title of a Microsoft paper about GPT-4, so that they're harbingers of perhaps human level or superhuman intelligence. Or sometimes you find this idea that they exhibit some kind of alien intelligence and that we can't really understand them at all, and this kind of Mysterian stance on language models. I think these claims are somewhat misguided, somewhat unhelpful, and I think what has emerged from the earlier talks today hints at a similar direction, because there is a rich middle ground between this kind of extreme dichotomy, and in the middle, we can try to use experiments, empirical evidence bring to bear to this question of the capacities we can meaningfully ascribe to language models. And so part of the reason why I think these claims are somewhat misguided is I think they look at the wrong sources of evidence. So there are two kinds of questions we can ask when we are interested in the capacities of language models. So first of all, there are first-order questions about their competence in different domains. And these are largely the questions we've been talking about today. Questions such as, do language models understand the world? Do they process representations compositionally? And for any competence X, analogical reasoning, theory of mind, planning, etc., do they have that competence? But there is a further question, a methodological question that we can call the second-order question. And that question is, how do we arbitrate these first-order questions about language models? And that's the question I want to focus on. Not because I'm not interested in the other questions, the first-order questions, and most of my work, in fact, is on these first-order questions. But I think to make tangible progress on the first-order questions, we need to tackle the second-order question. Okay, so here is the standard story about artificial neural network. Suppose you have a system that can receive as input 12 plus 54 and provides the correct output 66. We want to know whether the system is competent at addition, right? So in other words, we want to know whether the system produced the correct output because it applied the rule of addition, or for some other reason, either by chance or maybe because it's memorized this particular answer. With good old-fashioned symbolic algorithms, that's easy. We can just look inside the system, we open the box, and we see that we have this neat human interpretable algorithm for addition that uses bitwise operations that we can fully understand, and we fully understand how the algorithm went from input to output. We don't have any mystery about the competence question here. Now, the standard story goes, when it comes to neural network, this won't do because these networks are opaque black boxes. If you open up the box, what you find is a bunch of meaningless numbers, and you have no idea how to interpret this or make sense, head or tails, of these numbers to explain how the system has processed the input to produce the output. And therefore, the question is wide open. The system might have just memorized, the system might have just gotten lucky. We just don't know. Okay. So I'm going to challenge that story a little bit. So because of this black box view of neural networks, a lot of research on these systems just tries to think out of the black box because we're locked out, right? We can't look inside, so we just look at other sources of evidence. So where could we look? Well, we can take a look at the architecture. This we know what the architecture of the system is. When it comes to language models, they're based on this transformer architecture. So we can look at properties of the architecture abstractly and try to think about what that entails, about what capacities we could ascribe to them. That's really difficult and somewhat hopeless because we know that it's extremely hard, if not outright impossible, to predict from a given architecture what a trained model is going to be able to do, let alone what kind of competence we can ascribe to that trained model. And there are effects of scale, there are other effects that are sometimes unpredictable. We can look at the learning objective for language models, that's next token prediction. And this is what leads some people to say, don't say that language models can do X, Y, Z, because all language models do is next token prediction. And I think that's a bit of a sleight of hand, just because these models learn from optimizing a specific objective, which is next token prediction. And that's only during pre-training. These models are also fine-tuned with different objectives. Just because they learn that way doesn't mean that in the process of getting better at next token prediction, decreasing the loss, they don't acquire all sorts of abilities. So that's also a bit of a non-starter. We can constrain thinking about what they can do by thinking about the learning objective, but it's not going to answer all the questions. We can also look at the training data. That's also useful. That can constrain our thinking. But again, very hard to just look at an untrained model and its training data and predict what it's going to be able to do. There are certain questions we can only answer by looking at the trained model. Right? So what do most people do? Well, in this field, most researchers look at the behavior of the systems. And that's a lot of what we've been discussing today. So we perform experiments to see how the system performs on different tasks, behavioral tasks. All right, so of course there is a distinction that everyone is familiar with in cognitive science, and people might disagree on how significant the distinction is or how broad the gap is, but nonetheless there is this basic distinction between performance and competence, where performance is the visible part of the iceberg, the observable behavior of a system, while a system's competence is the kind of underlying abstract and often idealized knowledge and rule system or computations that enable and constrain an intelligent system's behavior, right? And so there is, in an intelligent system, an obvious relation between competence and performance in the sense that for a competent system, performance is the external manifestation of competence, at least if we idealize things a bit. The problem is, what do we do when we only look at the behavior of a system and we want to know, make some kind of reverse inference about its competence or lack thereof? So that's the challenge of understanding language models through behavior. I would argue later that this is not the only way we can tackle questions about the competence of language models, but it's certainly the most common and perhaps the easiest route. So there is a double dissociation we can draw that is often drawn in cognitive science between performance and competence. So it's certainly a distinction that is made with respect to human cognition very routinely. And the idea is we can't always make the positive inference from good performance to competence. Why? Because there might be cases of performance success despite lack of competence. And we've already discussed some examples of that earlier today. The idea is that, well, if you give a test to a student, the student might get a good grade on the test just by cheating, memorizing test answers, learning shortcuts, or the test itself might be badly designed. When it comes to humans, it is often believed that there is a dissociation in the other direction as well. In other words, we can't always make the negative inference from bad performance to lack of competence. Why is that? Well, because there can be performance failures despite underlying competence, and that is the case whenever there are contingent factors that interfere with performance and that are not due to the lack of competence, such as perceptual or motor limitations, inattention, working memory limitations, disfluency, underspecified test conditions, etc. There are many examples of that kind of thing in cognitive science, in psychology and linguistics. What about language models? Can we apply this dissociation to language models? Well, as we've already heard today, it's very common to apply the dissociation in one direction. We look at cases of success from language models, and we ask, is that really due to having the underlying competence we want to test for? Is that really, does the system really understand? Does it really perform arithmetic? Does it really have the ability to process representations compositionally? Or is there some kind of trick here, or some kind of shortcut learning happening? So that's the positive inference is often blocked. However, the decision in the other direction is often resisted, at least by people who are skeptical about deep learning and language models. So the idea here is that whenever the language models has some failure modes, make some mistakes, we say, aha, that's evidence that it doesn't have the competence. We don't say, well, maybe the mistake could be due to some other factor that's kind of this interference on performance. And the reason for that is that there's kind of underlying assumption that's often not explicitly defended that there is no equivalence to the kind of interference in performance that you find in human cognition or animal cognition in deep neural networks. And I will come back to that, but I think that's a premature assessment. Okay. So what are the kinds of behavioral evaluations we might want to perform to assess the capacities of these systems? We've already talked about this. You could perform qualitative evaluations, the infamous Turing test. There are various other modern forms of qualitative evaluations. But by and large, when it comes to scientific inquiry, we want to have more objective quantitative evaluations. So we can turn to benchmarks, which are often standardized and broad, wide-ranging, like these natural language understanding benchmarks we talked about. Or we can have some more ad hoc tests, sometimes one-off tests for particular papers that are expert designed and focused on a very specific task. But that's what I'm going to talk about, this category of quantitative evaluations, leaving qualitative evaluation to the side. Okay. So when it comes to these quantitative evaluations, there are various challenges to the positive inference from good performance, good task performance, to competence. And these have been already raised, in particular by the first two talks today. So first of all, there is this phenomenon which may or may not be innocuous, depending on the case, of benchmark saturation that Melanie has already talked about, where you have this increasing trend of new benchmarks being saturated increasingly quickly, meaning that new models reach human level or superhuman level within mere months, sometimes even weeks of the benchmark being created. So I'll give you an example from my own work. So a couple of years ago, Google Brain came up with this idea of organizing this massively collaborative benchmark, reaching out to a lot of researchers across disciplines involving psychologists, linguists, and philosophers, in addition to computer scientists, to try to assess the capabilities of language models, make the benchmark as hard as possible, and have a lot of different tasks in the benchmarks that relate to different capabilities. So with some colleagues, we designed a task for this benchmark. The benchmark is called Big Bench, that looks at conceptual combination. So the idea was to test if language models could flexibly parse conceptual combinations, combinations of concepts, and know how to apply them to a new context. So we have different subtasks in our task, but one of them, to rule out just memorization, makes up new words in the prompt. So you have a prompt, an input that defines two made-up words, and then you have 4 sentences that apply the combination of these 2 words together, and the system has to determine which of these sentences is the most likely, the one that makes sense given the 2 concepts. We also introduced some distractors, some kind of adversarial sentences in the wrong sentences to try to confuse the model to make sure it really grasps the conceptual combination. Now, initially, what was quite interesting is that among all the tasks on the Big benchmark, and there were over 100 tasks, this was one of the hardest ones for language models. So initially, the first results, all models, including GPT-3, were basically at random, and the average human was very good, and the best human was perfect. And then what happened? Google trained what was, at the time, the state-of-the-art language model that was before GPT-4. It was called PaLM 2, and this happened. And so the new model skyrocketed to average human performance, essentially, on the task. So that's an example of saturation, a pretty stark one. We go from 0 to not quite perfect, but human level. So So is saturation always a problem? Not necessarily, but it might be a symptom of some deeper problems sometimes. So having an explanation of the task performance when it's matched with human-level performance that assumes that the model has reached human-like competence on the task domain, that can be premature. We need to make sure that this is really the good explanation, right? So the clues that this is the wrong explanation is if you find some obvious failure modes outside the benchmark items or you play around with the system. And we've seen a lot of examples of that where a model does very well on a benchmark and then there's a blatant failure mode when someone tests GPT-4 in the ChatGPT platform or some other example in the same domain. So we need to map out the hypothesis space of possible explanations of the performance. And essentially, we need to interpret benchmark outcomes through an inference of the best explanation of the performance that is constrained by some sanity checks. Now, as I said, it's not always problematic because in the case of our conceptual combination benchmark or task, I actually struggle to see an alternative explanation of the good performance that would make sense given how we designed the task, that would not conclude that the system is able to parse novel conceptual combinations appropriately. And that's partly because we designed the task by introducing these, as I mentioned, these distractors and adversarial factors to try to check precisely whether the system was relying on shortcut learning or not. But I'm open to be contradicted if you find some plausible explanation. If you look at the task is available on GitHub, and the paper is published as well. Okay, but there might be issues, and so some of these issues that Melanie mentioned, that includes data contamination. So if you look at the technical report for GPT-4, OpenAI mentioned our benchmark Big Bench and says, during our contamination check, we discovered that portions of Big Bench were inadvertently mixed into the training set. So what happened is the results, the answers from the Big Bench benchmark leaked into the training data, and therefore we can't use that benchmark on GPT-4 because it's not meaningful. So that's an example where they at least they caught the leakage, right? But that's not always the case, as Melanie mentioned as well. So did they catch everything? Well, they reported a number of really impressive results on various tests, including human examinations and coding problems. One of them was a set of coding problems from code forces. It turns out if you test GPT-4 on coding problems from code forces that are after the cutoff date for the training of GPT-4, performance plummets. So that's probably another example that wasn't caught by OpenAI of contamination, where the system was just trained on the test set, essentially. And that's increasingly a problem because we train these systems on internet scale data. And so how can you demonstrably rule out the presence of benchmark items in such large data sets, especially when the data sets are not public? It's a big problem. So what are the solutions? Well, one option is to have a hidden test set. That's as the ARC challenge from François Chollet that Melanie mentioned does, but that's not perfect either because ideally you want your test set to be available to scrutiny from other researchers. And so doing things in secret behind an API is also ideally not how we want to do science, but unfortunately we have to do that sometimes. So another thing you can do to check for what we could describe as a kind of a broader form of contamination is counterfactual testing. So contamination goes beyond just brute rote memorization of test answers. It can also broadly refer to the memorization of patterns that are, or schemas that are extremely similar across certain benchmarked or quantitative tests and what's in the training data. And so if you don't have enough variations in your stimuli that you test on, that you test the models on, variations from the typical stimuli you would find in the training data, including in the tons of papers that the models are trained on, then that's a potential problem. In other words, language models may succeed on common tasks, but fail on trivial iterations that violate memorized patterns or use uncommon distributions. And so again, Melanie mentioned an example of a few examples of using this counterfactual stimuli that just make some alterations and see whether the model is robust these alterations. And that's one way to check for this broader kind of contamination or memorization. Okay. Another problem that's a little trickier to address because it's almost a kind of byproduct, sociological byproduct of how the field of machine learning research is set up, is gamification. So there is this perverse incentive in machine learning research, which is what's sometimes called SOTA chasing, state-of-the-art chasing, where you have benchmarks that have leaderboards and everyone is shooting for the top position on the leaderboard. And that's highly incentivized, for example, by big machine learning conferences, because if you can claim to have several percentage point improvements on the state-of-the-art on a benchmark, that usually makes it easier to get your paper accepted and published. And the problem is that here we have an effect of what's known as Goodhart's law in economics and other fields, which is that when a measure becomes a target, it often ceases to be a good measure. And specifically, the idea is that there are this class of failures that can occur when you optimize complex systems based on proxy metrics, which is what benchmarks are measuring, rather than the true underlying goal of the measurement. So the benchmark is supposed to measure a certain construct, certain competence, but in order to measure that construct, it's relying on proxy metrics, which are the test scores. And so the kind of statistical relationships that you identify from empirical observation that you use to construct a benchmark, to construct the proxy metrics, that will tend to break down when actively exploited and optimized, when you have this competition for these few percentage point improvements between 90% and 100% on leaderboards. So that's a concern as well. So what are the takeaways? Well, tests designed for humans, ideally, I say ideally because oftentimes that's not really the case in practice, but ideally they're designed to be meaningful because they're designed to measure some underlying competence that's meant to generalize to real-world situations, right? The reason why the bar exam is a useful exam is because we think it might generalize to some important competence for lawyers out there to do their work. And a given test can be valid for humans, but invalid for language models, and in fact, vice versa. So patterns of performance on a benchmark can only constrain inferences about competence given certain background theoretical assumptions. These are assumptions about the measuring instrument, which is your test items, also assumptions about the testing conditions, I will come back to that in a second, as well as assumptions about the target system. That's, these are common ideas from measurement theory and the philosophy of psychometrics, but they ought to be emphasized when it comes to evaluating LLMs behaviorally. So I talked about the reasons why we might not want to rush to make the positive inference from good performance to competence. What about the inference in the other direction? Well, as I mentioned, when it comes to humans, we often have that kind of attitude where humans make all sorts of grammatical mistakes. For example, it is a mistake of subject-verb agreements. And we don't conclude that humans who make these mistakes don't have linguistic competence. We explain away the mistake by appealing to some other factors. Maybe that person was tired, maybe they weren't paying attention, maybe they were distracted, etc. So we say it's a contingent error, and we block the negative inference. Now, when this kind of error is made by language models, usually the attitude is not the same. This is a symptomatic error of a lack of competence and kind of triviality of the computations that are performed by this system. So we do authorize that negative inference, and that choice is often not explicitly defended, even though it ought to be. So I will now mention one reason when it comes to behavioral tests that we might want to block that negative inference, and then later on I will talk about maybe deeper mechanistic reasons. So one big problem that is very common to find in other fields, like in comparative psychology, studying animal cognition, that we want to match conditions appropriately between systems that are very different, have very different motor and perceptual apparatuses, for example. So if you want to test how athletic different animals are, and your test involves climbing a tree, well, of course, you're going to stack the deck in favor of the monkey. But clearly that's a problem. You can't conclude from the lack of performance of, say, the elephant on the climbing tree benchmark that it doesn't have any motor competence, for example. So here's a case study in language model research. So there's this paper by Lacretz and colleagues from Stan Dehaen's group that looked at whether transformer can process nested dependency in sentences and approximate the competence of humans for recursion. So that relates to big debates in linguistics, but the idea is that you have structures with these dependencies, like, I don't know if that works. The keys that the man holds are, you need to agree the verb with the subject keys and ignore the subject in the nested clause in the middle. Lacretz and colleagues tested models like GPT-2 and found that GPT-2 could process short-range recursion in nested object-relative clauses like this nearly perfectly. But performance dropped below chance for the more complex cases where you add a prepositional phrase, like in the example B here, to make the embedded dependency longer. Right? And so in that case, GPT-2 seems to get confused and make the wrong prediction about the agreement of the verb. And so they concluded transformers are fundamentally limited in their capacity to handle long-range recursive nesting, okay, making that negative inference from the performance error. Does that hold up? Well, it turns out this is a classic case of unmatched conditions. So Andrew Lampinen from DeepMind had a nice follow-up experiment where he reproduced the results, but he observed that the human subjects in that experiment received substantial training with examples, instructions, and feedback, which is often the case in psychological experiments. And what about the models where they were just tested 0 shots? So you just give them the test sample and you want them to spit out the right answer. There is no equivalent of the training conditions that humans get. So what did Andrew do? Well, he added context analogous to human training by having a few shot prompt where you give examples of the tasks to be performed. And then what do you observe? Well, LLMs perform as well or better than humans, including on the most challenging constructions. Okay, so that's a good cautionary tale that we shouldn't be too quick to make the negative inference from bad performance to lack of competence, just like we shouldn't be too quick to make the positive inference. And it's good to keep these two things in mind. So general lessons to be drawn from these considerations, I think, about behavioral evaluation. I think we ought to take on board a set of best practices from psychology and cognitive science when it comes to the evaluation of language models. And that's a point that's been emphasized by the other speakers. We kind of need to build this new science of LLMs, not quite from scratch, but by taking inspiration from other fields, the study of human cognition certainly, but also fields like comparative psychology, the study of non-human animals, which has a lot of lessons to tell us about comparative biases. So what are some of the things we can do? We can use multiple observations for each evaluation item. We can use multiple tasks that test for the same putative ability to provide stronger constraints on our hypotheses. We can use novel stimuli. We should use novel stimuli when possible to avoid data contamination. We should also use, if possible, minimal stimuli to avoid confounds. We should adapt, importantly, the stimuli to language model-specific conditions because they can only receive text input to control for various quirks of the way they work, the fact that they can only receive text, but also things like quirks of tokenization that can greatly affect performance on things like arithmetic tasks, as well as training, whether we prompt them a few shots, 0 shots, and so on. We should use closely matched control conditions to rule out lower-level explanations. This mirrors what people do in comparative psychology to try to not jump to conclusions about high-level capacities when there is a simpler explanation of the animal's behavior. And importantly, we need a healthy dose of theory in the background to scaffold all of that. We need to justify the validity of the link between measure and construct, and too often you see people rushing to construct benchmark without really thinking about the construct validity of the target of the benchmark and how that relates to the test items. Okay, so That's for behavioral evaluation. I said behavior, when you think outside of the black box, is the main source of evidence we have to try to arbitrate these disputes about the competence of language models. Well, what I'll argue now, and that's a nice segue to Paul's talk, is that we can go beyond behavior to look at what trained models can do and how they work. We can try to understand language models from the inside. We can try to open up the black box through interventions. And contrary to the received view, we can actually do that, and we can find some very interesting, highly non-trivial results. So this line of research is heavily inspired by work in neuroscience. And one technique from neuroscience that has percolated in deep learning research is using probes. So you can train probing classifiers on the activations of your network and that you label with respect to a particular feature that you want to study, to find out whether certain activations in some layers of your network encode that feature. So for example, you can focus on a syntactic feature, maybe is your model encoding information about subject-verb agreements. You can train a probe to see whether that's decodable, that information is decodable from the activation of your network. And generally the standard here is you want a simple probe because you want to avoid confounds. So the probe should be generally a linear probe. And if your information is linearly decodable from the activations, then you can be reasonably confident that the information is at least in principle available to the system in there somewhere. The problem is that mere probing is purely correlational. You know the information might be available. You don't know whether it's causally efficacious in the system's behavior. In other words, you don't know whether that information actually has a downstream influence on the outputs of the model. And that's what you really want to know. We want to know how these systems process information and what information they process to produce their outputs. So what we need to go beyond mere correlational probing is to perform causal interventions. And that means we need to intervene on the parts of the network that we assume are encoding and processing certain types of information based on what we can decode from them, and see whether we can manipulate them and see what is the downstream effect on behavior. And if we see a change on behavior that is consistent with the hypothesis about what that part of the network is doing, that provides us much stronger evidence that the system is actually making use of that information. Okay. So there are all sorts of techniques that have been developed in the literature. There is this emerging field of mechanistic interpretability research that has a number of interesting results. But there are other people coming from different perspectives that use similar methods in computational linguistics and also other groups. Unfortunately, sometimes these people talk past each other because they use different terms for the same techniques. But by and large, the main tool that is used in that field is what's known as interchange interventions, also known as activation patching or causal scrubbing, has different names. But the idea is the following, very quickly, the basic idea. You can run your model on an original input that's related to a behavior of interest, in that case, predicting or spitting out what the capital of a country is. And then you just cache the activations of your network in the forward pass when it's processing that input and producing the output. Then you run the model again on a different input that produces a different output that creates a change in behavior. And then you rerun your model a third time with the same same input as the alternative input, the second input, except that you swap in the cached activation from the first run on some part of the network. And if you see that the output changes and that you can restitute the original output, that tells you that this part of the network whose cached activation you've swapped in seems to be causally responsible for producing that output. That gives you information about the causal structure of the network. That's the general idea. There are lots of variations on that, and we don't need to get into the details here. Okay, so just curious, how much time do I have roughly? 7 minutes, okay, great.
Or as much as 12.
Right, okay. So I'm just going to use 3 case studies of this line of work and show some examples of what we can find out about neural networks, transformer models in particular, in this way. So here's the first case study that looks at the mechanism that identifies the indirect object of a sentence. Suppose you have a sentence like, when Mary and John went to the store, John gave a drink to, and the model has to output Mary. Well, you can use this kind of approach to try to reverse engineer how the network is going from this input to the output by finding out, tracing a circuit inside the network across different layers. That's a kind of algorithm that is interpretable and explains how the network is attending to different parts of the input in different layers to produce the output. I'm not going to give it, we can come back to that in discussion if there is interest. I'm not going to give a full explanation of the algorithm that was discovered, but we can do that, and this has been reproduced in several other works, and all the results are convergent. There's this clear algorithm that emerges, and importantly, that's all learned through the kinds of mechanisms that Paul has discussed earlier. Attention heads in the transformer architecture get specialized to performing different functions and can compose into this kind of algorithm. Here's another example. There's this nice paper that trained a network and transformer model from scratch on a modular addition task. So you have A plus B modulo something, and found out through this same kind of approach that the network, once it was trained well enough that to be able to generalize quasi-perfectly on the test set, had actually learned an algorithm to solve modular addition. And that algorithm, it's quite clever. It relies on trigonometric identities. I'm not going to get into the details, but you can fully describe it. And it's, again, this is an empirical discovery. It's not something like when you a priori from looking at the architecture. You just looked at the trained model, and it turns out that this is the solution that it converged on to reduce the loss on this next token prediction for this particular modular addition task. Not only that, but we can actually study the training dynamics of this model, which is really interesting, because what we find is there are 3 different phases during training that can be quantified. I'm not going to get into too much to the details of how that's done, but essentially what you see is initially you have a drastic reduction of the loss on the training set, the blue line. That's the initial memorization phase, where the model is just, neural networks are lazy, so they initially use shortcuts. So it's just memorizing input-output mappings, and it gets great performance on the training sets. But then it undergoes transition phases. First, it starts forming, as it keeps training, it starts forming a circuit to solve modular addition in a generalizable way. And that's when the performance on the test set starts to improve a little bit. And then it cleans up what it has memorized. So it forgets all the cheap tricks of memorization that's no longer needed, because now it has this generalizable algorithm for modular addition. And that's what you get drastic improvements on the test set and almost perfect accuracy on the test set. So that's really interesting, because it goes against some of the orthodoxy about neural network, and certainly against this kind of stochastic parents view that all they do is memorization and that they can't generalize. What is true, though, is that neural networks may not generalize or acquire general solutions to problems if they're not forced to. And what forcing them to mean could mean have diverse enough data, train for long enough. There are various components to that idea. Okay, and a third case study that's relevant to the question that was asked earlier by Melanie about whether language models could, in principle, understand the world, is this nice series of papers on a model that was trained on a game of Othello, which is this very simple board game where you have to, when you occupy a tie, to surround your opponent's positions, and you can convert them to your color if you do that. So again, a mechanistic study looked at a network that was trained on sequences of moves from Othello until it got almost perfect accuracy at predicting legal moves. And it turns out that you can have probes that can linearly decode the whole state of the board at any given time step in the game from the activations of the network. which speaks to that idea that, at least in this toy model, it might be that the network can acquire some kind of representation of the world in the game world, at least. And furthermore, you can intervene on these representations. So, for example, you can intervene on the encoding of information about a specific tile of the board, and as it were, make the model believe that this is a tile occupied by the current player, and that changes the model's predictions about legal moves, right, accordingly. So you can do this kind of counterfactual intervention. Okay. So back to language models. We can't always generalize from results in toy domains with small transformers to language models, of course. Increasingly, there are results using the same techniques that are now scaled up and automated on much bigger models that are very promising, and some of them have already confirmed some of the findings with smaller models like the induction heads that Paul mentioned briefly. So there is, as I've argued, compelling mechanistic evidence that language models do induce algorithm or algorithmic solutions to certain tasks. But there is, of course, also, as we've discussed throughout this event, plenty of compelling evidence that language models and their behavior is not purely driven by neat, interpretable algorithmic solutions. And so I think both behavioral and interventional research suggests that we should reject this kind of fallacious forced choice between the idea that language models either just memorize or I just develop neat algorithmic solutions and have this kind of perfect generalization, right? In fact, instead we have this kind of pluralist view of language models when part of what they do is memorization. Memorization is very important to various tasks. Language models have to recall a number of facts, just like we do, and so for that you just need memorization. Memorization is not always a problem. There are all sorts of heuristics that these systems used that are not quite general content-independent algorithms, but are more flexible than just memorize input-output mappings. And finally, there are these more rigid and abstract algorithmic building blocks that they can induce. So I think these three things can cohabitate in the same systems. You can have these task general, row-like algorithms in some domains that are helpful in some cases, which may be composable. You can have your heuristics using flexible pattern matching that approximate various functions in certain distributions. And you can have input-output mapping and memorization like a lookup table. So again, when we say that good performance can occur despite the lack of competence, well, we could say maybe that's due to interference of things like heuristics and memorization, right? How about the negative inference? Is it always valid? Can we conclude from bad performance to lack of competence? Well, I think we can't always do that because precisely you can have that interference of heuristics and memorization on the causal efficacy of algorithms that the network has indeed learned on behavior, at least on certain inputs. And in fact, there's also some research showing that the same network can develop multiple parallel algorithmic solutions to a certain problem that might sometimes compete or get aggregated at the output. I could say more about this in the discussion or maybe panel, but I think that's something that gets us closer to an analogous analogy to this idea in humans, that you have, if you want to call it that, different modules or different factors that may compete with each other in the influence and performance. And to tie it back to human cognition, though this is a meeting on cognitive science, we find these interference in humans too, right? This is well known from psychology. We have these content effects on reasoning, where you fill in the details of various inference or reasoning tasks like syllogisms, the Watson selection tasks, and other problems. When you fill in the details with plausible everyday life content versus abstract content or nonsensical content, humans are much better when you fill in the details with plausible or daily life content. And the same is found in models. There's a good paper by DeepMind that shows just that. Language models show the same trends in the content effects on reasoning as humans. And there are other papers that go in the direction. I don't have time to go into the detail, but there are this collaboration that's going going to be preprinted in a few weeks, hopefully, with Eli Pavlik and some of our students at Brown, where we look at semantically guided structure mapping in analogical reasoning, in contrast to some earlier works by Melanie or Webb and colleagues that look at this more kind of abstract, purely syntactic form of analogical reasoning. And here, too, we see that language models can match human performance. And so there are, I think, deep reasons for that when we think about cognition, and I will conclude in a second. The deep reason is that cognition involves trade-offs. And the trade-offs might not be the same, of course, for language models and for humans. I'm certainly not suggesting that human cognition and language models have this kind of one-to-one mapping that would be ludicrous. But there are trade-offs that might look roughly similar. So you have trade-offs between efficiency, flexibility, and structure. If you have too little structure in your system, that might undermine flexibility in the sense that your system might not be able to generalize properly. For example, in arithmetic, it might just memorize input-output mappings. And that also threatens efficiency. There are tractability concerns. And if you have too much structure, something like a classical good old-fashioned algorithm, that also undermines flexibility because it's not going to be able to flexibly adapt to noise and uncertainty and distribution shifts, and as well as efficiency. So we need to find that sweet spot, and human cognition has been fine-tuned by both evolution and development to kind of find some kind of optimum for these trade-offs. And language models and other deep learning systems had to find in very different conditions another optimum with slightly different trade-offs, but the general idea, I think, shows this kind of convergence on trade-offs. So in conclusion, to address this second-order question, I think we need both well-designed behavioral experiments that take on board good practice from cognitive science, as well as this kind of nascent interventional research that take inspirations from neuroscience. And we can chip away at the first-order questions from both ends, both from top down, starting from some theorizing about capacities and how this construct might be operationalized in behavioral tests, and from the bottom up, looking at the basic mechanistic building blocks of computations in the systems. And this is not only useful to understand language models, which is interesting in its own right, but it's not what I'm most interested in. I think this is also useful to help sharpen theories of cognition, specifically thinking about the computational building blocks of cognition generally. And I would have more to say about how exactly we can take on board some insights from deep learning to constrain thinking about human cognition, but I will leave it at that. Thank you.
Thanks for the lovely talk, a great summary of so many themes that were discussed today. We are, over time, and we're heading right to a panel with Q&A. So let's take a 5-minute break. We're going to come back. We're going to come back at 3:40, so that's actually an 8-minute break. We'll come back at 3:40. We'll start the panel. Start thinking of your questions that you would like to ask your panelists. We'll start off with Rick Lewis engaging with the panel, and then we'll open it up to you guys. After the panel is the reception. Again, everybody's invited. Thanks, Raphael. Lovely way to sum everything up. Loved it.
Thank you. Hi.
Thank you so much for your talk, because I'm also very interested in the mechanics interpretability and also in logical reasoning. So, but one of my questions is that I think it might also be an issue in neuroscience that when you are trying to perform mechanistic analysis to models, you actually need to analyze case by case.
time.
Are you working on this?
Well, one of my students just like, he read the Othello papers and he was very skeptical, so we started doing some like. I'm good right now.
Okay.
Gotcha.
Great call.
Chocolate?
Oh, sure.
Well, he was skeptical that.
Good idea.
How much
It will get me going.
world model?
How are you holding up? Is your lack of
There's
sleep?
like a couple
Oh.
hypotheses. One is that
entirely?
yes, transformer learns a world model that you can code from the
Yeah, barely.
The other one is that
Hi, folks. Please make your way back to your seats. Great. So we've now entered the panel session portion. After that series of amazing and thought-provoking talks this morning and afternoon, I'm sure people are ready to dig deeper into these issues and generate some conversation and crosstalk among our speakers. Our moderator is Professor Rick Lewis, the John R. Anderson Professor of Cognitive Science, as well as Professor of Psychology and Linguistics, who's been engaged at the intersection of cognitive science and AI for, let's just say, a couple of decades, and was the former director of the Weinberg Institute from 2017 to 2023, leaving me with very big shoes to fill. So I've made these reminders before, but before we start, just a reminder, the reception immediately follows this panel session, so join us for that and continue the conversation. And with that, I hand the microphone over to Professor Lewis.
Thanks, Chandra. And I just want to echo again and thank the speakers for a spectacular slate of talks. It's been really, an extra round of applause I think is worth it. Yeah. I feel like I have the extraordinary privilege to interview the dream team after the Olympics. But this is not, I don't want this to be an interview. We don't want this to be an interview. We want it to be a discussion. So I'm going to lead off with a question that I hope all of you might weigh in on, and then feel free to ask each other questions, and then we're going to open up to the audience with questions as well. So I want to hearken back to the two talks this morning, which I think identified a number of, you can think of them as sort of failure modes of these new large language model-based systems that I'm roughly going to summarize as failures of common sense of some sort, failures of abstract reasoning, even kinds of elementary kinds of abstract reasoning, failures to understand what can be generated. So some of these are a bit surprising, maybe. So I want to get the panel's take on the diagnosis of these problems and get your speculations on what might be the missing critical ingredients. What is the secret sauce? So let me put a little bit of structure on this. So one answer, maybe a kind of default big AI lab answer, is these things will just resolve themselves with higher quality data, basically with the kinds of ideas we have out now, prediction-based learning, transformer-like architectures. Once we get video prediction into the mix, these things will, resolve themselves in short order. Another response might be, no, there's something critically insufficient about just prediction as a learning goal. That might be one. Maybe we need explicit goals to learn causal models. Another response might be, no, without embodiment of some kind, without a first-person rich sensory motor stream, these issues will not resolve. Another response might be, without other kinds of architectures, maybe of the kind that Paul was starting to lay out, that impose sorts of inductive biases for compositional abstract capacities to emerge, we're never going to get there. So those are just some ideas about what the critical missing ingredients would be. And I'm casting this as an AI question, but of course it's also kind of cognitive science question, what's the secret sauce for human intelligence? So that's the lead-off question.
So, great question. I think for any problem, especially for intelligence, building intelligence, it's likely that you can get good performance in several different routes. And so human intelligence takes one route, and then AI takes another route. And as far as benchmark performance goes, it looks great in many cases. In fact, finding common sense errors with the GPT-4 can sometimes be hard unless you know how to break it. So, a lot of people come away with this impression that these models are really amazing. But when there are multiple routes, sometimes these routes can be seemingly correct for the wrong reasons, which Raphael also talked about in his talk. So it could be that the models found some shortcut, different ways of seemingly performing well without really acquiring deep conceptual understanding about the world. And so then, what's the missing piece? I think embodiment probably helps a lot, but just throwing images and video data on top of the current generative AI models will not cut it, because the learning objective itself is not quite right to begin with. So adding more data of more modality will not just solve the situation, address the situation, because the learning objective right now is, by and large, predict which word comes next or predict which pixel is missing, as opposed to make sense of the world. So the thing about human learning is that I don't think we try to learn by predicting which word comes next. We try to rather make sense of the world. We ask questions. We try to experiment with the environment. We interact. We make hypotheses. I mean, even babies, they make hypotheses, interact with the environment, because they're not that interested in some sense, predicting which word comes next, but they're interested in making sense of the world. And we don't yet know how to really translate that into a learning objective that can also scale successfully. So until we figure that out, with or without embodiment, we'll probably suffer with the same problem.
Well, I basically agree with everything you said. So I'll just add a few things. I think that babies, it's interesting that the way that large language models learn is, in some sense, the opposite of the way babies learn. Babies learn first non-verbally by interacting with the world, by trying things, as Yejin said, intervening, trying out new things, doing experiments, being little scientists in a pre-verbal way. And they learn about these, I talked about these notion of core knowledge. They learn about the basic physical concepts and social concepts before they learn about these very abstract adult-level ideas, whereas large language models learn the exact opposite way. They are trained on predicting the next word in very sophisticated texts, like those that you might find on Wikipedia or in book corpora, and they then are supposed to somehow come up with an emergent concepts of the kind that babies either start with or learn very early on. And it's just a strange thing that, to think that kind of reverse learning would actually work. And I'm not that convinced that it will. But just to follow up on one other thing, an interesting thing that people found, language models, you know, back in GPT-2, GPT-3, et cetera, were text only. And they had some failings, and a lot of people hypothesized, well, you know, the concepts they have, the words they have are not grounded. And giving them like visual input and multimodal inputs and being able to deal with multimodal data will ground them much better and will cause their performance to improve. But that actually didn't happen. You know, the fact that on many benchmarks at least, the adding of multimodal data did not result in improvement over the text-only data. So I think that the idea that the learning objective maybe is not the right one, at least for this kind of grounding, is probably correct.
I don't agree that it's a great question. Sorry. With all due respect for the preeminence that Rick Lewis brings to this discussion, I alluded to this at one point in my talk. Engineers always say, hey, that's broken, we got to fix it. And as a scientist, I want to say, hey, that's working, we have to understand it. And the thing about, I'm repeating something that you said last night, more or less. So it's not a correction to your dear colleague, but stealing from his playbook. The fact that any of these skills emerge from predicting the next word is miraculous, okay? It's not what they can't do, it's what they can do that is amazing and deserves scientific understanding. And so if we ever understood why predicting the next word allowed them to do what they can do, then maybe that would give us a hint as to why it isn't enough to get them to do what they can't do. But by no means should they be able to do what they can do. Nothing that we have studied, learned as cognitive scientists that I'm aware of, would lead anybody to expect that a system like a transformer would produce spectacularly good English syntax and solve the problems that it can solve. So I do think that as cognitive scientists, as opposed to engineers, we have the luxury of asking about what works and why, and hope can be placed in the possibility that when we understand why what works, works, then we'll be in a position to understand why what doesn't work. But nonetheless, in all seriousness, I do think that the fact that this learning objective, which makes no sense to anybody, I mean, I'm a linguist more than I'm anything else, and which isn't saying a lot, but I'm a linguist more than anything else. And when I first encountered the idea of a language model with my colleagues in the speech recognition group at my university, I just broke out laughing. What do you mean, a language model is something that tells you what the next word is going to be? Come on. We linguists know a lot about language, and that has nothing to do with what we know, okay? Almost nothing to do with what we know. So much so, the fact that doing so allows a model like GPT-4 to learn so much about the structure of English that it produces fantastic syntax, which we can't come close to generating with our grammars, is just mind-blowing to me. Rather than asking, what is it that this objective is missing, I'd like to know, what is it that this objective is finding that I had no idea was there to be found? So the ability to predict the next word is helped by knowing some syntax. You know that the next word is likely to be a verb, but that doesn't take you very far. And you know if it is a verb, it's going to have to agree in plurality with the subject, but that doesn't take you very far. And knowing what the topic is doesn't take you very far. Nothing takes you very far. It's a whole bunch of very, very, very poor cues that go into guessing what the next word is. Yet somehow, it produces beautiful English. That's amazing. So there's something about this learning objective that I don't get. And it's not what it's missing, it's what it's got.
Personally, by the way, I like the pushback you have because it's very spicy, I'll give you that. But personally, I don't find it maybe as surprising as, GPT-4 is very impressive, especially after RLHF, how much it can do better than the raw language models. But when I look at the raw language model performance, smaller model performance, even like, by the way, let's roll back a little bit. GPT-2 is perfectly capable of generating already fairly grammatical sentences. And that was, for me, the wow moment that this works really well. But when I saw that, what follows afterwards is not that much of a surprise in terms of the generative capacity of these frontier models. Especially when the learning objective was predicting which word comes next, and then especially when it was trained on such large amount of data and model with very large context size. And at that point in time, I kind of agree with Ilyas Oskiver's position, which is that, well, in order to do well on the job, you kind of have to reverse engineer a whole lot about why on the earth which word comes next, which actually not only relies on grammaticality of language understanding, but also some aspect of world model as well. So all of these things are not exclusive from each other. These are all mixed in the data. And the fact that we train this simple model that can really scale up, because it's the simplicity, we can scale things up so much, and then these models can learn such rich patterns, doesn't surprise me too much. Like, I am surprised rather by the engineering capacity this, OpenAI has, and then the extent to which they're willing to push it. But the fact that it does work so well seems to make more sense to me. But when I think about the failure mode is when I get to think about why it's making certain failures, why certain problems are trivial for us, but it's suddenly so hard for GPT-4, is when I think about the main difference between my learning objective versus language model's learning objective. The fact that we don't focus so much about the surface patterns in some sense and focus more about the world model might really bless us to learn about concepts, as opposed to, for language models, any concept is a token. In fact, we never know how the numbers are even represented as different tokens. And there can be all sorts of weird artifact or spurious behaviors coming out of that as well. So I do still think that there's something, I should maybe also take more constructive angle to that as well. But when we look at failure mode, we also get to learn a lot about the main weaknesses of current AI models.
Yeah, I just want to say quickly, I think we need to keep distinct the engineering goal of AI, which is just to build systems that can perform some various forms of intelligent behavior, and then the goal of cognitive science, which is to model human cognition and non-human animal cognition. And these two goals can come apart. From the engineering perspective, whatever works, works. It's a free-for-all. If OpenAI could build a good model that's just a giant lookup table, they would, and that doesn't matter as long as the product is good, right? But if we're interested in modeling cognition, then we ought to pay attention to certain factors such as, is the model learning from a plausible amount of data that's in a realistic learning scenario with the right learning objective, and et cetera. These two goals could converge. It could turn out that the best way to build a good AI model is to take inspiration from cognitive science. But I think actually the trend has been over the past 10 years of deep learning research, that there are very little insights from cognitive science that percolate into deep learning research, for better or worse. But I do want to emphasize there is, to just follow up on the point about infants and how they learn, there is quite a lot of work from academia, from people who come from a cognitive science or computational linguistics background, on trying to model human language acquisition or human learning with deep learning models, but not the big, opaque, giant models like GPT-4, much smaller models that are trained from scratch on a realistic amount of data in a plausible learning scenario. So for example, there is this competition called Baby LM, or Baby Language Model, that includes a corpus from child-directed speech, so actual speech that was recorded, that's spoken to a child, that has the same amount of words roughly as something like an 8-year-old would have heard. And the output, the first results from this competition is that models that were trained on this corpus actually did learn syntax quite well. And so that's starting to put a dent in kind of poverty of the stimulus argument from traditional kind of generative linguistics. And then on the question of multimodality, there was recent work from Brendan Lake and others that use these head-mounted cameras to record the visual and audio stream of experiences that an actual child has. And you can train a model on that kind of data. And actually, there are very recent results that they published in Science showing that having the information from the visual stream also helps to bootstrap some of the performance of the model in the linguistic domain. So I think when we actually consider the realistic data from developmental psychology and not this random internet scale data that OpenAI uses, we start to see things that can be useful as plausible cognitive models or model learners that we can use in cognitive science.
Great, thank you. I want to just briefly offer a defense of the prediction learning task as a nice idea for cognitive science, because given that it does yield these amazing capacities at some level, I think we all have to grant that, as Paul was pointing out, it's a beautiful task because it gives you signal at every moment. And there's actually a lot of good evidence. In fact, some of the leading ideas in language processing now are basically predictive models. And even developmental psychologists depend on the fact that babies are making predictions with their violation of expectation paradigms to do their work. So it's clear that even infants are making predictions. So I'm actually thrilled with the idea as a basis for building really interesting cognitive science models. I want to ask one more version of my bad question, and then we'll open it up to the audience. It's a related question. It's not the same question. So Yejin was just, I think, pointing out the possibility of multiple routes to intelligence. And while I'm excited right now about the interplay between cognitive science and AI, I can also imagine a future where there is a real divergence, simply because the human system, like the child, is facing a different problem. It's limited data, it's embodied, very limited data, and that the solutions, all the things that some of the things we've been talking about, like inductive biases and the architectures, those will all be very important for cognitive science, but maybe they're not going to be important for AI, and the fields will actually diverge. Any thoughts on that possible divergence?
I mean, I completely agree. That's, in fact, if you look at recent language models, we've already passed the point where language models are better at next word prediction than humans, if you actually test human predictions on whatever words come next. So we've already passed that point of divergence in some respect with respect to one particular aspect of human performance. And so, yeah, and the same applies, of course, to the kind of data the systems are trained on. And there is this other question of whether we might get somewhere in deep learning research by just building one giant model trained end-to-end that can receive multiple modalities as input, text, images, videos, but also maybe actions or joint torques, proprioception, and so on. And maybe that's the future, that's one future of robotics. Now, is that the future or the best way to model something like cognition, where some people think that maybe we need different models that talk to each other, right? We need modules. That is also another area where it might turn out that we can converge on very different solutions in the domain of AI and in cognitive science. So yeah, I mean, I agree.
I agree too. I think that the fields could very much diverge, although there might be some pressures to keep AI systems more human-like, because as we deploy them and have them interact with humans in a way that they need to sort of understand the world the way we do, and in order to be able to work with us and communicate with us. But I do think there's multiple paths to intelligence, and in fact, I was talking with some of my colleagues at the Santa Fe Institute who work on astrobiology. And there's a very good analogy between astrobiology and AI, because in astrobiology, they're trying to ask, what would life be like on other planets? And it wouldn't necessarily be anything like us. It wouldn't necessarily have DNA or anything like that. But there are some principles of information and information sort of propagation through that have to hold. And so I think one of the things that AI is going to help teach us are sort of what are those sort of really basic principles of intelligence. And that, I think, is a really exciting thing.
This is really good question. I had to think a little bit to imagine how much more divergent can it be. I thought it's already pretty divergent between the two fields. And I think there are two possibilities. One possibility is that, as you said, AI really doesn't need to worry about data scarcity. It should perhaps always make use of internet data from day one. And as a result, it will always be large data driven. And in fact, maybe there's no other solution, even as the truth of science, maybe the other solution just doesn't exist. That's one possibility, in which case, despite smart people trying to find that solution, nobody will succeed. That's one possibility. Another possibility is that there exists a solution. It's just that nobody yet figured it out. No human being figured it out. In large part because we're not willing to even try, because we all think that right now the only way is large-scale data way or large-scale compute way. So we're not seeking the alternative path. So then what happens? Let's suppose that nobody's figuring it out, but there's still a possibility that the data-rich direction eventually reaches superhuman level performance, and that AI might figure out, oh, wait a minute, there's actually cheaper, more data efficient way of doing another AI that can learn like human babies do. So we don't know which one of these will be true, but since we don't know, I think we should try both ways, is my personal take. One last thing I want to add is that we tend to think that in many ways human intelligence is superior to AI. But nonetheless, if we teach human babies in the way that we teach AI, meaning supply the baby with broadband, show lots of New York Times articles, one after the other, don't allow the baby to ask any question, and zero freedom about the curriculum selection either, I don't think human baby will actually figure things out. That, to me, is really fascinating potential clue to think about different alternative paths.
Thank you.
Sort of. Yeah, I think it echoes at least what Melanie was just referring to. And so cognitive science, in many people's minds, is the study of cognition, in the abstract, and not just human cognition. And it encompasses cognition of other kinds of systems, including artificial ones. And so everything that AI learns about what can be done with gigantic training corpora is informing us about the theory of learning in general, and what we learn about, what it takes for animals to be able to learn what they need to learn is not necessarily going to be informative of what our babies are learning, but it's all part of what the big tent is supposed to be about. So you could say that the trajectories that you're talking about maybe shouldn't be thought of as divergence, as just sort of further diversification within cognitive science.
Completely endorse that. You're reminding me how I'm betraying my own most deeply held beliefs in my questions to the panel. I think this might be a good time to open it up to the audience, if there's a way to get microphones there.
Carl over there have microphones. Keep your hands up, please.
Hi, so forgive me, I'm a little bit out of my element. I'm mechanical engineering undergrad, so if my question's a little bit flimsy, then know that I'm just trying my best. But from what I understand, so with large language models, one of the most interesting parts to me is this idea of emergence. And hopefully I'm not misrepresenting it, but I think some researchers from Stanford kind of are pushing back against this idea that we should be surprised that as large language models get to a certain scale, they exhibit certain capabilities. With an example similar to what was given in the first talk of math operations, that if you assign partial credit, then you actually see this capability beginning to occur. And that, I guess similar to the sand heap philosophical question of when does it stop becoming a sand heap as you remove grains of sand, I'm not sure that anybody would say that, one neuron is going to make the difference, but is it appropriate to think of, whether it's a neural network or some other structure, that there's a minimum amount of information carrying units required to perform specific tasks, or is that paradigm or way of thinking of things maybe misaligned or not appropriate? Sorry for the length of my question.
I agree with your interpretation. This is very hand-wavy, but my personal speculation is that this all boils down to information. How much of information can we learn? How much of information did the data even provided to begin with? And so in my talk, I had this component where I would try to synthesize AI data. And the act of it, at the end of the day, is for me to provide a lot more different, diverse data that internet doesn't have, and increasing just the quality of the data considerably for the target task. So one can increase the information by just putting more data, which is OpenAI way. If you think about how alternative path there could be, there may be like different data scheme, textbook scheme, declarative knowledge that's somehow different from internet data, but I think it all boils down to information. And then in order to carry out that information, there has to be probably some minimal size neural network for the amount that we need to train. And I don't think it's super well understood what the minimum should be, but at least the scaling laws papers give you some correlation between these two things.
Thank you. Thank you.
Hi everyone. Hi everyone. So we are in this interesting space where AI systems can be superficially right, but at the bottom of the task they can be wrong. But it's also incredibly difficult to verify whether they are right or wrong. Let's say, for example, take a healthcare setting, or let's say when we are taking help writing a program. They can write a program which might seem to work, but then there can be a very small bug which can be very difficult to verify. So from the standpoint of deploying these systems in the real world, what implications does it have? And how do we think about this, like when it's incredibly difficult for people to verify, and also in high stakes decision, people don't have the time to verify their outputs. Like how do we imagine this scenario? Like how can we safely deploy these systems in the real world in this kind of a situation? Thank you.
Well, I don't think you want to deploy these systems autonomously in those kinds of situations, at least not until we figure out a way to do more sort of make them more trustworthy and verify them better. So I think that's something that, people talk about the risks of AI. One risk I think that is very important is the risk of people using these systems in situations for which they're not trustworthy. And that's going to happen more and more since people are, they're both susceptible to marketing from big companies that are selling the systems, and also they themselves are, the systems are extremely good and very convincing that they're going to be reliable. And there's kind of a trade-off between when a system gets to be very, very good, but not perfect. We humans tend to give it more autonomy than we should, and you see this with self-driving cars too. That once they get to a level of quality, humans stop paying attention and let them drive themselves, and then they sometimes can get into trouble. And I think we're going to see that more and more with AI systems.
I 100% agree. I want to actually add one more thing, which is that the question hinges on this concern that maybe we will have a harder time evaluating the future AI that seems to be great by and large. And I am quite worried about that personally as well. It also reminds us of this Anthropic paper about scalable oversight, where it may be that neither AI nor humans can really reliably evaluate AI systems in the coming years. And currently, the evaluation research is considerably lagging behind the speed of progress of the frontier models, especially people in academia. I think we can definitely invest a lot more into what to do about it. I don't think it's as simple as just asking lay people to evaluate AI systems success and failure mode, because it's going to become just increasingly hard to evaluate quite right. And it's likely that we need to innovate on the HCI aspect of it, innovate on how to even design the benchmarks in the right way. And it's likely that we need to get some algorithmic help as well to make it easier for humans to evaluate somehow.
Hi. So I have two quick questions. One for one of the questions that was being asked before about interactions, or how these models are being trained with this next token prediction objective. I guess technically speaking, we shouldn't be just talking about the training protocol, right? We should be also talking about the inference protocol. For example, we don't just often ask a zero-shot computation from the model. We might use some of the more fancier inference algorithms like star, quiet star, all of these interesting algorithms, which do allow the model to take a step or use some external verifiers, then think about do you find this step that you just took amongst 50 generations you made, which one did you think was the best, and then adaptively improve upon it. And overall, in some sense, that's an interaction with an external verifier, which is enabling you to further and further improve what you're trying to produce. In some sense, in this whole pipeline, interaction is involved then, right? And especially if you account for the in-context learning abilities, possibly the model is learning from what it is doing. And even when you account for RLHF pipelines, even in the training protocol, we could argue that interaction is happening already. So I'm just curious about your thoughts on that. And just to add a second quick question, piggybacking on what Raphael was talking about in regards to performance versus competence. I think we often don't have like good definitions when it comes to like evaluations of whether it's machine learning models or humans in general. And like as a theorist myself, I often think about that like when it comes to like talking about fundamental limitations, which is more or less what this whole symposium has been about, like unless we define a concept, it becomes very difficult to like talk about the inexistence or existence of that thing, like concept grounding. We still don't know, like from a mathematical standpoint, when it comes to like talking about like can a transformer be grounded in this multimodal domain that I have? Like unless I can define it, I just have no clue how to get started on it. Unless I can define what a capability or a concept the word means, it's hard to get started on it. So I'm just curious about your thoughts on that as well. Like where do you think like a definition, like what would a definition look like to you in the context of like a machine learning system?
Okay, I can just take the second question. Yeah, agreed. So that's why I think we should chip away at the first order question I said from the top up and the bottom up, meaning we need to do the theoretical work to, we start with these anthropocentric concepts of capacities because our reference point is humans, right? And we humans, we kind of carve out the space of our cognition into these cognitive kinds, which are things like reasoning, theory of mind, etc. And then we can go ahead and ask about non-human animals like corvids. Do they have episodic memory? Do they have a theory of mind? And we can do the same thing with our systems, except there is no shared evolutionary history. So first of all, we need to kind of question whether we can apply these categories as they are to these systems. And I agree that there are all sorts of challenges there. My approach to this is that we ought to, and that's a problem that cognitive science has been working on for many decades. Once we start from the folk psychological category, kind of break them down and see whether one kind of clusters of properties they involve, and what are plausible computations involved in securing these different properties. And then we can go ahead and look at systems, including artificial systems, and see whether we find anything resembling these computations. And if we work at the problem also from the bottom up, so I didn't talk much about compositionality, but like Paul, I'm very interested in that, and specifically also figuring out whether systems like transformers can perform variable binding, represent variables independently from their values and bind variables to values and have kind of role-filler independence. And this is like a fundamental building block of cognition that we suspect, many people believe, is key to many things we can do in cognition, regardless of how you decide to carve out, at the high level, different cognitive kinds, space of different cognitive capacities. So I think that's why I think we can chip away at the problem for both ends. We need to have this conversation about cognitive ontology, different kinds of cognitive capacities that may or may not be applicable to different systems like language models, and also figure out what are the kind of computational building blocks of both human cognition and artificial systems, and see whether there is any convergence and see whether things cluster in the same way. And they might not cluster in the same way, in which case it might be a misnomer to speak of theory of mind or episodic memory in a very different system that doesn't have these clusters.
Maybe I can answer the first question. So you're right that RLHF or inference time, chain of thought reasoning, especially in interaction with other verifiers, does feel like some form of interactions. And it does help the performance. Compared to human interactions, while humans are learning, including children, although it's a form of interaction, there are several things missing, but I'll just highlight two of them. One is that the way that LLMs interact is more passive in nature, whereas human interactions can be a lot more active. Like we might even ask questions, whereas ChatGPT right now can only answer questions. The other related but different angle here is that humans have a better epistemic awareness about what they understood and not. By the way, I'm slightly, careful about this because we all know that humans not necessarily are fantastic at it either, but at least humans have some notion of whether they understood something or not, and they think they know something or not. I think LLMs, just by design of next word prediction, is not really encouraged to think about what it does know and not know. It's some unfortunate byproduct of setting the learning objective just about that. And then, some folks just hope that, somehow magic arises when you have a lot of layers of neural network, that it's going to try to make sense of the world accidentally. But because it's not trying to make sense of the world as its learning objective, I don't think it's really encouraged to think about what it doesn't know. And that does make a big difference in the quality of interactions that it's going to have with the world.
Hello. My question is about the scalability of large pre-trained models. I guess language is a very concise and abstract form of the world that humans use to communicate with each other. Now, if we want to extend that and ground it into the multisensory world and train a model with multimodality, then the computation cost can scale explosively. For example, just to represent a single 5-letter word, APPLE, that costs 5 bytes. But at the same time, a picture of Apple, 128 by 128, that will cost 5 kilobytes of storage. So imagine if a large language model with 170 billion parameters doing an okay job with reasoning, then in order to incorporate multimodality, that would be at least 1,000 times more, but then plus more in-depth context reasoning or incorporate the other modalities. I don't know how large the model will have to be in order to process all of this information. Another small calculation I did is if Meta indeed run their 600K H100 GPU for 1 whole year, it can actually feed 4.33 million human adults, assuming everyone consumes 200 calories per day. So my question is, where do you see AI models go in the next 5-10 years? At what point will we run out of money to buy more GPUs or pay for the energy consumption? And how much intelligence are we actually getting out of these models compared to human adults? And how many of these AI products is actually reliably applicable for our daily life when every once in a while it will throw out a surprise answer? Thank you.
That's a fantastic question, and I think it's really important set of considerations that we all, as citizens have to really think about. What do we want from these AI models? And what are we willing to give up? What are we willing to pay to get that? And what kind of value will we get out of them? I think there is a trend towards smaller models. People are starting to understand how these incredibly huge, perhaps even multi-trillion parameter models can be compressed. And I think there will be a trend towards smaller data requirements. So Raphael mentioned this baby LM experiment with a much, much smaller data, sort of pre-training data set than ChatGPT. It was able to still accomplish a lot. But even still, these systems are ridiculously expensive in terms of energy, other kinds of things, human reinforcement learning from human feedback, getting so many people to have to label these outputs and so on. And I don't know, we have to really think about, is it going to be worth it? And I'm not totally sure it is. So I don't think that, AI, these companies kind of present this to us as an inevitability. AI is going to be everywhere. It's going to be the new electricity. It's going to power all of our, everything we use in our lives and all of our jobs. And I I think there should be some pushback at that narrative of inevitability that is being, in some sense, forced upon us. And it's something that really worries me.
About the multimodal models that might need to be even larger, although I haven't been tracking the size of current multimodal sizes closely, I believe that they're much smaller than large language models, not because, it might be that compared to the amount of internet data available and the amount of information that needs to be processed, currently it looks as if there's not as much of a non-language data to require a lot larger models, but that doesn't mean that the size is not going to blow up. I actually worry that Sam Altman will raise $7 trillion. And with or without doing that, not only OpenAI, but other tech companies will rapidly try to advance all of these scaling bottlenecks. And I expect that we will see orders of magnitude larger models just because. Don't feel relaxed about, oh, maybe data will run out. No, data will not run out as easily. I think it's likely that there's a lot of hidden data, harder to access on the internet that can be unlocked if you have the will and money. But also one can synthesize a lot of data as well. Altogether, I think probably at least one order of magnitude more data, but probably more like 2 orders of more magnitude data available. And then there can be more GPUs being produced, currently primarily by NVIDIA, but of course other companies in other countries will also catch up on that. And in fact, I suspect there will be hardware innovation as well so that things can actually run faster with less energy. But the moment it's like less energy, other people will spend more energy anyways. So I actually worry that this is unstoppable train. And this is very much non-zero possibility, that's significant possibility, I should say, not non-zero. That's going to happen. And in that context, what can academia do? I think we have to fight hard to find the alternative path that's not as data and compute intensive, because otherwise there's going to be major concentration of power. Only the richest tech companies can afford to do that, and there's nothing healthy about it, seriously. And in the meanwhile, people, as Melanie pointed out, there are some growing research trends for small-scale things, but they tend to be more like academic in nature. And it's not like they're really catching up on the capabilities in an aggressive manner. And I worry about that we're not trying hard enough. And the academia, as well as small startup companies, small companies in general, we all need to work together. And that's where also open source becomes so important. We need to work together to find an alternative path that's not just relying on large language models.
Hello, I believe I'm the last question. I'll be very brief. I'm one of the unlucky few people to work in evolutionary computation for my PhD, so that's artificial intelligence without training data. My question for you is that evolutionary computation can produce answers with true novelty because they discover through error, effectively, through mutation based on evolution. My question for you is, if LLMs can only produce novelty through emergent properties, where do you see, from a cognitive science perspective, the future of discovering novelty outside of training data? Because at some point that won't be enough, in my opinion, and I'd like to hear your thoughts on that. Thank you.
That's a great question that I don't think computer scientists understand well about the scope of the creativity, what AI can and cannot generalize out of the training data. And one crude way for me to try to explain that is interpolation versus extrapolation, but it's a very hand-wavy way. And when I say this word, some people react as, oh, I get it, and then some people are like, what do you mean by this? Like, define that mathematically. And I mean, like, they know the mathematical definition of interpolation and extrapolation. It's just that in the context of what LLMs can generalize and cannot generalize, or what DALL-E can generalize, that DALL-E can generate avocado chair, even if it has not seen it before, it feels like more of interpolation to me, but it's not very clear how to clean-cut define it. But in any case, I found that when I talk to different people, some people believe that there's no limit as to how much you can generalize and create original data points out of LLMs, whereas some other people feel like there's a fundamental limit. And again, this is a sign of us as a community not having enough of insight about how to even reason about the scope of creativity, which requires a lot more research. So I'm sorry that I'm not giving you any satisfactory answer here, but I personally speculate that there's a limit in the type of pure, like genuine creativity that we might see from these generative AI models in the current form. And if that's true, I think it's actually a good thing for humanity so that we have some upper hand. I mean, not everybody is equally creative, but at least we feel like there's some people out there who are creative enough to beat over ChatGPT. Whereas if that's not true, then just we are all around inferior.
Yeah, just to follow up. So, these systems can generate a lot, and I think it's you may know the story of the Library of Babel, where every possible sequence of words is generated in a book, and there's just books and books and books, and the problem is, how do you find the good stuff? And right now, humans, these systems can generate, but they have a hard time judging, and that's a big part of creativity as well.
All right. What a fantastic panel. What a fantastic discussion. You've started the applause, but I just want to say that today's talks were terrific, complimentary, and stimulating. And I want to give a big round of applause to Professors Millière, Mitchell, Smolensky, Choi, and big thanks to Rick Lewis for moderating the stimulating panel. Please. A little bit of crosstalk there. There's other people that need to be thanked. An event like this is a big undertaking, and it takes a lot of people. I want to give a huge thanks to the Weinberg administrative team. Some are here. I saw Carl Abrego here earlier, and Jen Wynn over there, and Megan Matisic outside. Val Murphy provided lots of administrative help. And one person stands out in having really organized everything. That's Mackenzie Rafus. Is she here? Well, let's call her in. Mackenzie organized all the details and made this whole event flow so smoothly. She also brought her artistic touch to it. If you look at the program, you look at the website, you look at the poster, that's all Mackenzie's aesthetic eye. So let's thank her and the whole Weinberg administrative team. We'll be back again next year, and given the enthusiasm, I've got a good feeling that AI will be a centerpiece of what we do. So please keep us in your plans. With that, our day is done, and the reception awaits us. Everybody's invited. Thank you all.